Okay. Okay, looks like we're live now, so let's get started. Cool. Oh, it's good to see many people here. I hope the pandemic is not taking a worse turn, but last time I said this, it was 2020 in February. Yeah, I was talking about the nanopore sequencing engines that are shipped to China at that point in time. I think I gave a picture of that in February 2020. I don't know if people realize that the importance of it at that time, but that's critically important to understand the pandemic for sure. And then I think we didn't have a lecture after that. Maybe a few lectures after that, I don't remember. But hopefully today will be different. Okay, so today we're going to cover the fundamentals of multiprocessors. We've been covering multiprocessors clearly in the past few lectures, but I wanted to also give a fundamental treatment of it since it's important. Since everything we build today are multiprocessors. There's really no interesting system with a single processor today. Everything is multi-core, and on top of multi-core, we have multi-node systems. So many processors in our lives. In our cell phone, for example, we have 16 plus processors right now, right? And these are some readings. You may have noticed that this homework has more readings this time. We assigned 5 required ones, but 2 of them are really easy. One of them is this one, Amdahl's 2-page paper, which should be really easy to do, and we cover it also. And the other one is, I don't remember what the other one was. Oh, that was Lamport's sequential consistency paper that we're going to cover in the second part of today's lecture. But I have some recommended readings also here. These should be in PDFs on the course website. Were you able to find them? Did anybody look for? Okay, good. Because sometimes those PDFs are not linked, so we should link them. Okay, and we're going to talk about memory consistency also. And tomorrow, probably we won't get to it today, but tomorrow we'll talk about cache coherence, which is an important topic in multiprocessors, clearly. But let's start multiprocessors. And before we start multiprocessors, it's good to have a taxonomy of computers. And this is a seminal paper that was written by Mike Flynn in 1966 that categorized computing systems into essentially 4 categories based on how they handle instructions and how they handle data. So you can actually construct a 2x2 matrix in terms of classification of computers, in terms of whether they execute single instruction or multiple instructions. I'll call them instruction streams. And whether the instructions operate on single data elements or scalar data elements or multiple data elements, which is more like vector, a collection of data elements, if you will. So imagine this 2x2 matrix. If you have this 2x2 matrix, one corner of that matrix is single instruction, single data computers, which is essentially single instruction stream computers that operate on scalar operations, which is very similar to what you had built in digital design and computer architecture, right? It's a single threaded architecture in a sense. Hopefully that's clear. SIMD, on the other hand, is you still have a single instruction stream, but each instruction operates on multiple data elements. And this is also what we have seen in digital design and computer architecture. These are vector processors or array processors, SIMD processors in general. Each instruction doesn't operate on 2 single operands, but each instruction operates on 2 vectors, for example. So your registry file looks like vectors right now, and you can do vector addition using a single instruction, for example. Or you can multiply 2 vectors using a single instruction. And this exploits data level parallelism because each vector may consist of, I don't know, 1 million elements each. And one instruction can specify 1 million operations. The same operation, of course, applied to 1 million different pieces of data or different pairs of data if you're doing multiplication or addition, for example. And hopefully that makes sense. And clearly GPUs are a prime example of SIMD processors today. But even GPUs have scalar portions, right? It's good to keep in mind that today's systems are more heterogeneous, but GPUs are mostly SIMD. MISD is interesting because now you have multiple instructions or multiple instruction streams, if you will. And they operate on a single data element. It's a bit harder to imagine, right? You have a single data element. How does multiple instruction streams operate on it? Well, a single data element goes into one instruction stream, and it gets operated on and get transformed into some element, data element prime, for example, and that gets communicated to the next instruction stream. That transforms the data element into an element prime prime, and that gets communicated to the next instruction stream. That transforms the element to another element prime 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 prime, well, prime 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 3 times, and so on. And the best example is the systolic array. You also saw this in digital design and computer architecture. It's also called a streaming processor sometimes, but systolic array processor does exactly that. You send the instruction, you have elements that are executing instructions, and you send the data from one end, and that data gets propagated through the elements and eventually gets transformed after some number of instruction streams operate on it. And we talked about doing matrix multiplication using a 2-dimensional systolic array, for example. And this is very good for convolutions in general. And these are used for machine learning accelerators today, as we discussed also in digital design and computer architecture. So I think the closest form of multiple instructions to single data is systolic arrays. And these are concepts that are developed in old times, right? And today we're going to focus especially on multiple instruction, multiple data. Essentially, you have multiple instruction streams, and they operate on multiple data streams, if you will. They could be completely independent. And this leads us to multiprocessors or multi-threaded processors. Does that make sense? I've gone through it relatively quickly. If you read this paper, the terminology is actually a little bit different, but they actually give a very good historical perspective from 1966, from 1966's perspective, if you will. So these can be completely different instruction streams operating on completely different data. They have nothing to do with each other, potentially, right? Although they may be solving the same problem together, right? They may be cooperating or they may be completely independent. Okay, any questions on this? Yes.
Yes. So why did the systolic array process die out, or why was it not popular compared to, let's say, SISD or SIMD? For instance, Cray really picked up the SIMD approach when Cray designed the earliest supercomputers, whereas SISD was, it was everywhere basically. But MISD was like, we don't see many examples for now. So
well, we see a lot of machine learning accelerators right now, right? A lot of machine learning accelerators are based on systolic array architectures today. Like the Google's TPU is essentially a big systolic array. They call it the matrix execution unit, I think, MXU. But it's essentially a big systolic array.
I was just wondering why it didn't get popular.
Why wasn't it as popular as the other ones you're asking, right? Yeah, historically. Yeah. Well, I think the execution model is more specialized, right? If you think about it. SysD is, you can write any program with SysD. You could argue that that's the way we're thinking about computers. Like one Neumann model is SysD, fundamentally. One Neumann model says you have a sequential single instruction stream, right? Each instruction gets executed before the other one. Well, each instruction needs to complete before the next one, and the sequence should be executed, right? Fundamentally, it doesn't allow any sort of parallelism, if you will, instruction level parallelism. So fundamentally, one Neumann model is not compatible with MIMD, right? If you think about it. Of course, it's easy to make it compatible. We're going to talk about that issue in the next part of the lecture. So SysD is a very general model. SIMD is slightly less general, data parallelism. We're going to talk about these also, actually. So maybe wait for some more slides. But if you look at MISD, it's not as general. Right? The number of problems that you can translate into MISD is not a whole lot. You need to think hard about, or maybe put it another way. If you have a problem at hand, and if you want to express it in MISD, you need to think extremely hard about it, unless the problem really fits. So these were proposed in late 1970s, early 1980s by H.T. Kung and Charles Leiserson. And they basically proposed as specialized architectures for convolution execution, for example. And they basically showed there are other applications, but these specialized architectures are really good for executing convolutions and similar mathematical operations relatively fast, filtering, for example. The downside is not all of the world is convolutions and filtering, even today, right? So these are good accelerators, but it's hard to think of them as more general purpose models. Does that make sense?
Yeah, thank you.
Yeah, and clearly MIMD is very general. It's parallel execution. but it's harder to do than SysD. So MIMD is also quite popular. Any other questions? Okay, maybe we should have a history of computing course at some point. It's a lot of fun to think about why some things have been successful, why some other things have not been successful. Of course, there are non-technical reasons sometimes, right, why things are not successful. But I think here it's clearly the scope of problems you can solve with a model. Or you can easily express. Maybe solve is too strong of a word, right? You can always say, okay, the way we think today, we can easily solve problems with SysD. But the way we think today, maybe our thinking is not very well compatible with MISD, right? Maybe 10 years later, people will think in different ways, and maybe they can translate everything to systolic computation, right? I don't know. It's a bit hard to imagine for us, but again, this is science and research. Maybe someone will come up with some transformation that can enable easy expression of problems on this sort of architectures. Okay, so basically parallel computers, right? Actually, parallel computers is parallel computation is a little bit hard to define, right? What is parallel in the end? I mean, even in SysD computers, we saw techniques that can parallelize execution, right? We talked about auto-ordered execution, for example. So we can have instruction level parallelism. So parallelism is actually everywhere. Even SysD computers are parallel, I would say. But traditionally, these are the computers that are called parallel. I'm going to talk about different types of parallelism in a couple of slides. But before we go into different types of parallelism, let's define parallelism. Parallelism is really doing multiple things at a time, right? It's a very fundamental concept. It's not just applicable to computers, right? It's applicable to humans, right? I'm moving my hands while I'm talking right now, and that's the parallelism. I'm also moving myself, right? So basically, things could be instructions, operations, tasks, etc. Many, many things. And why do people want this? What is the main goal? Anybody? Yes? Save time, basically performance, right? Improve performance. It's either time or throughput, right? Execution time is clearly governed by Amdahl's law. Keep in mind, we're going to get back to Amdahl's law. So by parallelizing things, hopefully you're going to save time or improve throughput. Any other thoughts? So that's I would consider a main goal. But that's not the only goal, actually. There are other goals for exploiting parallelism. There are 3 other ones, at least. Yes. Okay, maybe someone is good at talking on Zoom. No?
Design simplicity. Sometimes it's easier to express things as multiple worker threads than having a bunch of very complicated things like sequentially.
Okay, yeah, maybe I would call that, and it's somewhere here. I have a long bullet that covers simplicity, cost, scalability, etc., things that are related. But yes, I think certainly that's one of the reasons, and that's the reason why we went to multi-core from single core, right? Because it was very difficult to scale single core engines. It became too complex. It was a lot easier to actually have multiple parallel units, parallel cores that are much simpler, each of them, but hopefully you would get the performance of a single core, or even better than a single core, because you could exploit the parallelism using software. Yes?
Using what we already have. For example, we have probably 10 laptops in this room. We can do parallelism because we have them.
Yeah, sure. I mean, I would say maybe that's related to scalability, right? That's not a, that's not a fundamental goal on its own, but you're exploiting what's around you to improve perhaps performance, right? But I'm looking for what else can you improve? So I think the points that both of you have are kind of related. Yes.
Fault tolerance.
Okay, yes, that's certainly another point that's somewhere here. So you want to improve fault tolerance, right? Why? Because if you have 1 unit and if it gets a fault, what do you do about it? But if you have 2 units, if one gets a fault and if the other one doesn't get a fault, if they're executing exactly the same thing, then you have an idea. Oh, something went wrong. If you have 3 units and you're executing exactly the same program on 3 units, one gives you a different answer than the other 2, then you can basically say, oh, I'm going to vote between them. I'm going to pick the most popular answer. So basically, having parallel execution units enables you to tolerate faults better. And this is because you can enable redundant execution, right? Redundant execution in space in this particular case. There's also redundant execution in time. You can have a single unit, and you can execute the program once, and then you can execute the program twice again, and then compare the outputs, right? So that's another way of doing it, but there are some undesirable effects because you may be executing the program in different times, but that can also avoid faults. Okay, what else? There's one more thing over here. Yes.
Maybe when you're running approximation algorithms, you can run it parallelly on multiple cores and then take the best answer. So you're reducing the probability of failure and increasing the probability of getting a better answer.
I see. Okay. Yeah, I didn't think about it that way, but I think it combines multiple of these. You want to improve performance of those approximate algorithms by exploiting this, I guess, better redundancy that you have in hardware, right? Maybe you're taking advantage of both fault tolerance aspect and performance aspects of those algorithms, and the fact that algorithm is amenable to it, right? Very good. That's a good point. Yes.
Maybe flexibility, if it's easier to introduce a new task in a parallel architecture rather than to fit it in a sequential one.
Okay. Yeah, certainly, I guess. What are some example tasks that's the case?
I guess I was just thinking about threads. Like if you wanted, like that way, like if you were spawning threads in response to some kind of like input from the external world, right? Right. Then like if it's like using the parallel thread execution model would be maybe easier to do it.
I see. Yeah. Basically, if there's some natural parallelism that you have in the environment or the problem, having parallel computers makes sense, right? But in the end, the goal is really performance, perhaps, right? Or something like that. Or maybe simplicity. It goes back to your point about simplicity earlier, right? Because the way it's handled in a single processor is if some event comes in, you have to interrupt what's going on, right? The interrupt-driven models actually develop because you have a single processor. It's very unnatural if you think about interrupts. Well, it may be natural, right? If you think about humans, we get interrupted and we switch to some other task. So if you have a single unit, interrupts are the way to handle these events. But if you have multiple units, there's no reason why you need to interrupt one of them, right? Because somebody else is free to do the task. So I see your point about simplicity, but you could also argue that that's good for performance as well, right? Overall performance. Yeah, sure. Yeah. It's a very good discussion, actually. Yes, one more.
Yeah, inherent requirement to do two things at the same time. For example, we need to drive the car and look out for passengers, and you really don't want to stop doing that for, I don't know, keeping the engine going.
Yeah, sure. I think I would argue that that ties to your performance or goals in quality of service. But yes, sure. Again, I think this is similar to the problem at hand. You have a natural parallelism that you want to exploit with parallel computers. Yes.
Maybe energy consumption. It might be cheaper to run. If you're running for k units of time, it might be cheaper to run it on k over n smaller processors, exactly. Units of time down on k units of time on a big processor.
Yeah, absolutely. Basically, I think you covered. That's the last one I was looking for. Essentially, reduce power consumption or energy. The way it depends on how you express it, right? As opposed to, let's say, as opposed to having 1 unit at frequency f. Let's say you have 4 units at frequency f divided by 4. That's one example. Or you can multiply with n as I show over here, right? Why would this save power? Clearly, it's lower frequency, right? Each, well, maybe this is the place where we could do this over the board. So what was I supposed to do over here? You guys remember? Always have a hard time. Anybody? I share. Okay, share screen. Say it again. Something external camera. Yeah, exactly. Yeah, this one, content from second camera, I think, right? But not this camera. This camera. Okay. Let's see. Yeah, basically power consumption, right? If you remember the power equation, I think at some point we covered this. There's some activity factor and then capacitance, voltage square, frequency. I guess I used capital F, so let's keep it capital F. So as opposed to having 1 big unit that is supposed to be at frequency F, which requires, let's say, voltage V. I have 4 smaller units. I just picked the number 4 here over here, but you can derive an equation. Each of them is F divided by 4, and maybe corresponding voltage divided by 4, right? Because you don't need, if you want to clock a circuit at lower frequency, you don't need as much voltage supporting it. Yes.
Is this is an approximate equation, or is this a fundamental electrical?
This is fundamental, assuming fundamental voltage scaling rules apply. But today it's actually very difficult. If you're at a point where frequencies are extremely high and your circuits are extremely small, these scaling equations don't work as much. This is actually called Dennard scaling. Dennard is actually the inventor of DRAM, by the way. He also came up with a lot of technology scaling laws. And basically, he said that as technology nodes scale, we can increase frequency and increase voltage, or correspondingly reduce frequency and reduce voltage, basically make those trade-offs. But at very small nodes, unfortunately, this becomes very difficult because voltages are too small today, for example, to power up a transistor. If you want to reduce voltage even further, and also reduce frequency even further, your transistors break. They may not operate because you may not have enough voltage going into the transistor. But at some operation mode, it's very fundamental, yes. And this is one of the reasons why energy is becoming a bigger problem, because the scaling, let's say, has stopped at very small technology nodes because you cannot reduce the voltages further because that affects the reliability of the transistors. That's a very good question. Meaning this may not work very well as you go to much lower technology nodes. But I think this has worked so far. So if you see this clearly, the power of this is, well, C V square F, and the power of this parallel unit is going to be C. Oh, I keep doing this. And you can see that this is 64x lower power, right? And that's a lot. So there's a cubic relationship between frequency and power, because voltage also is tied to frequency, unless you go to extremely small technology nodes. And this is the main reason why multi-core made a lot of sense. Basically, it was very difficult. First of all, it was very difficult to build a single, let's say, core machine at high frequency, high voltage. It was a lot easier to build this thing. It would consume less area so that you could gain parallelism. It would be lower power at the same time. But of course, this requires you to be able to perfectly parallelize your program, right? If you really want to take advantage of that 64x lower power and not lose performance, you want to perfectly parallelize your program such that your program, let's say your program takes t time over here. Each of them is supposed to, well, hopefully, what am I supposed to say basically? I guess each of them should really take t time over here also, right? It should not increase. Makes sense, right? Because you're running four times smaller. In the end, you should finish at t because you have 4 units. Okay, so if you have imperfect parallelization, then what if this takes 2t? Now you're wasting some energy. It may be still okay because you're earning at much lower power, right? But there is some point where your energy waste is too much, right? And 2t may not be tolerable, right? Clearly, you had a processor that was t at this point, and you replace it with a processor that's 2t. Who's going to buy that processor, right? For those applications that are not perfectly parallelizable. And that's the dilemma of parallelism as well, right? If people are very used to this model, single core, even though this may be extremely power efficient, it may be not good for performance, right? Make sense? Okay, cool. Any other questions on this? Okay, let's move to stop sharing your screen again. So that was the power part of the parallel computation. Again, keep the caveats in mind. It doesn't always work. So it's going to go back to the lecture that we had last time, right? If you can't perfectly parallelize your program, which is the case, then these benefits are not as perfect as you wish. Okay, the second one is, I think, the point that I mentioned, right? You can improve cost efficiency and scalability and reduce complexity. Basically, the arguments several of you have been making put together. It's harder to design a single unit that performs as well as n simpler units. So why not, assuming that your program is parallelizable again, why not design the n simpler units? Overall, you would improve your cost, you would improve your scalability, you would improve your complexity, you would reduce your complexity compared to a single unit. And maybe some of those units already exist, as you mentioned, right? They're all around us, right? Just exploit that parallelism that already exists. Okay, and the last one I think is improving dependability, redundant execution in space that we also talked about. Anything else? I think this covers all the points we discussed. Maybe this is not as clean as the other 2 points, but I think they're intimately tied to each other: efficiency, scalability, and complexity, or cost efficiency in particular, not energy. Okay, so then as I mentioned, there are different types of parallelism and different ways of exploiting them also. Parallelism is a very broad concept, right? And we've seen a lot of instruction level parallelism exploitation concepts in digital design and computer architecture. There's data parallelism and there's task level parallelism. Just to remind you, instruction level parallelism is, I don't know why this is not moving. Different instructions within a single instruction stream can be executed in parallel, right? And we've seen many examples of this. Von Neumann model fundamentally doesn't allow this, right? It's the interface. It's basically a contract, and it says that an instruction should not be executed before the previous one is complete. Pipelining is a very simple microarchitectural technique that breaks down that, right? You can pipeline instructions, which means that portions of instructions are executing in parallel in the pipeline. You can do out of order execution, you see that. You can do speculative execution, VLIW model, superscalar execution, and then the data flow models. These are all instruction level parallelism. We're going to get back to data flow in the next lecture. Hopefully many of you remember this. If you don't, you can actually look at the digital design and computer architecture courses, because we cover instruction level parallelism quite heavily in that course. We cover data level parallelism also, but data parallelism, as we discussed, different pieces of data can be operated in parallel. And SIMD and systolic arrays are examples of this. In SIMD, you're operating on different pieces of data using a single instruction. Single operation is replicated essentially on different vector elements. In systolic arrays, you're transforming. You can also think of, well, if you have a systolic array like matrix multiplication, you're actually operating on multiple different pieces of data. Each of them is going through some systolic transformation. And finally, the last one is task level parallelism, which is different tasks or threads can be executed in parallel. And multi-threading or multiprocessing architectures are a good fit for this one. So we're going to especially talk about this today. But as you can see, these different things can be combined, and they are combined in our systems, right? Even instruction level parallelism systems have SIMD units today, and many systems are multiple instruction, multiple data. But let's talk about task level parallelism. How do you create the tasks? And there are clearly 2 ways of going about it. We've discussed both of them. One is running many independent processes together. They already exist. Different users have different problems. You collect them on a single multiprocessor and run them together. It's called batching of the jobs, for example. And here you're exploiting independent processes. Whereas the first one is to improve a single problem by creating multiple related or cooperating tasks. And clearly this leads us to parallel programming. If you do this explicitly, meaning you have a program or you have a problem and you want to divide it into multiple tasks, then you need to do some parallel programming. Tasks may be natural. In that case, it's easier, potentially, right? I don't want to call it completely easy, but for example, web queries. Many different users are sending queries to your system and you want to handle them. Those are natural tasks. They may need to communicate sometimes with each other, but those are natural tasks. But it's difficult when the natural task boundaries are not clear, right? And we will discuss that. And we've seen examples of it in the last lectures clearly. This can also be done completely transparently, right? This is a difficult thing to do, of course. Meaning you have a single problem, you write you rewrite a single-threaded program for it. And you say it's somebody else's task to parallelize it. And somebody else, maybe the compiler, maybe the hardware. And this hardware and the compiler transparently, implicitly, takes your single-threaded program and ships it to multiple processors. Makes sense, right? That's always done today, which is not true, unfortunately, because this is a difficult problem to do, actually. This is called thread-level speculation. That's the general name of this sort of technique. And the idea is make programmers' life easier again. Somehow the compiler or the hardware parallelize a loop, for example. The programmer provides a loop, and the hardware says, oh, okay, I think I'm executing loop iterations. Let me execute this iteration on this computer or on this core. Let me execute the next iteration on this core, next iteration on this core, etc. Now you're executing multiple iterations in parallel. Of course, this works if you can really execute them in parallel. And you have to check whether what you've done is correct. That's why it's called speculation. Basically, you're creating these threads speculatively, implicitly, without the programmer's knowledge. Programmer may potentially provide hints, but they're not going to parallelize their program, because otherwise that would be the first part, right? Explicit part. They provide hints to you. And in the hardware or the compiler, you create these threads, and you need to check whether what you've done is correct. So how do you check whether what you've done is correct? Well, whether the semantics of the result actually matches what the programmer actually intended with the single-threaded semantics, right? And that boils down to ordering of operations and whether you get conflicts between different threads, right? Does that make sense? So if you're updating some data in an order that's completely opposite of what the programmer specified, then you're probably doing the wrong thing. So certainly this is possible to do, and there are a lot of research, actually, there's a lot of research that went into it in both compilers and architecture to try to do this. And unfortunately, it's not easy to do, basically. The benefits that you get are not as high as the benefit that you would get if you actually explicitly parallelize your program. Okay, I'm going to mention some later lectures. Probably we're not going to be able to talk about this in this class because we don't have any lectures left. But I think this is still an interesting problem. My feeling is it's very difficult to do unless you have a lot of help from the programmer. Okay, the last one is the easiest one, let's say. Whenever there are many processes that you can collect from the outside, they exist. You can run independent processes or tasks together, right? Batch simulations are a great example. Multi-programming was developed actually to exploit the parallelism across different users and programs. And clearly cloud computing workloads take advantage of this, right? There's huge amount of parallelism across users, different users. They don't interact with each other, basically. And the downside, of course, is this is great for throughput, but doesn't improve the performance of a single task. If you care about a single problem, and if you want to improve the performance of it, too bad, this doesn't help you. Right? Okay. Any questions so far? Yes, please.
For the transparent level parallelism, is it called transparent because it's that way for the hardware? Because I was thinking from a programmer's perspective, it'd be like less transparent, or it wouldn't be transparent at all.
You mean this thread level speculation? So from the programmer's perspective, it's transparent, right? Programmer writes ideally, the programmer writes a single threaded program. They don't care about like creating threads or tasks. And the hardware or the compiler underneath says, okay, I'm going to break it into smaller tasks and execute those smaller tasks in parallel in multiple cores, let's say. So from the programmer's perspective, it's completely transparent. Hardware or the compiler does a difficult job of parallelization.
Okay, I think I'm just a bit confused about like it's like I think usually like when you say like is an organization transparent, you mean like can you see like can you understand what's going on behind the scenes? That's why I guess that's what I was thinking when I heard the word transparent.
I see. Well, the way I use the word over here is the programmer doesn't need to do anything basically. The parallelism or task creation and management is completely transparent to the programmer. They may not even be able to understand what's going on basically underneath, because the illusion should be that the program executes just like a single-threaded program. That's the illusion hardware and the compiler should provide. Yeah, exactly. Yeah, very good. I mean, there's been a lot of research actually in auto-vectorization, for example. Can you automatically vectorize programs that the programmer didn't vectorize? That's another example of this. It has had limited success. There are auto-vectorizing compilers, for example, that were researched in 1980s, 90s. High-performance Fortran is one example. Unfortunately, it's limited to programs that the compiler can really perfectly analyze. If the compiler cannot analyze, disambiguate different memory accesses, for example, it cannot parallelize or vectorize the program really well. Yes?
Do you have idea about what is the state-of-the-art thread level speculation? Maybe just speed up.
Oh, speed up. Okay. That's a difficult question. Because in many of these cases, well, it depends on the program. That's always true, right? It also always depends on the workload. But the average speed up you get is not a lot, basically. And I don't want to venture any numbers, but numbers like, and it also depends on the number of processors, but usually these approaches don't scale to very large number of processors also. Going from, let's say, 1 to 4 processors or 1 to 8 processors, you get 50% or 2x speed up if you're lucky. And that's not a lot, right? But if your program is like really nicely parallel, of course you will get a lot of speed up probably even with this, but usually that's not the case.
I think this one is a really interesting technology because clearly it may not get as performance as the explicit one, but if you get this boost for free, then why not?
Yeah, sure, exactly. And that's basically the argument also, right? If the programmer doesn't do anything, you have this idle hardware sitting around, why not, right? Well, one reason why not is it's waste energy, of course, right, with a lot of hardware. But if you don't care about that, then it may be okay, right, potentially. If your goal is to really reach high performance without burdening your programmer much, why not? And that's one argument for this, sure. And of course, these transparent implicit techniques usually work much, much better if the programmer follows discipline, right? Meaning they use library code, again, which clearly delineates what could potentially be parallelizable, what could not. But if they do something wrong over there, then again, you're back to square one. Okay, well, we've seen this also when we talked about bottleneck acceleration last time, right? If the programmer follows some disciplined synchronization primitives, they use libraries, it's a lot easier to accelerate that code. It requires some effort from the programmer, but not as much effort as explicitly partitioning the tasks. Okay, now let's jump into a little bit more fundamentals of multiprocessors. Clearly, there are different multiprocessor types, and this is 2 general types, loosely coupled and tightly coupled. Loosely coupled is essentially similar to what you said earlier, right? All of these processors already exist. Let's enable them to cooperate and work with each other. No shared global memory address space, basically. That's the key distinguishing factor. This is also a computer network, if you will, programmed using some sort of communication mechanisms between them. Basically, that's the biggest distinguishing factor, whether multiprocessors have a shared global memory address space or not. Tightly coupled means these multiple processors share a global memory address space, and they can do loads and stores on that shared address space. Whereas loosely coupled is each of them has its own address space, but they have other communication mechanisms so that they can communicate data with each other. And loosely coupled is essentially a multi-computer network-based multiprocessors with some communication mechanisms between each other so that they can potentially solve a single problem divided into multiple tasks. Whereas tightly coupled multiprocessors are really what traditional multiprocessing is about. It's also called symmetric multiprocessing for historical reasons. But existing multi-core processors and multi-threaded processors are almost all tightly coupled. There is a shared memory exposed to each processor. The address space is shared, and as a result, this address space also gets reflected to the programmer. Programmer uses shared memory program. Maybe I'll distinguish them later on if we have time, but keep this in mind. And usually, the loosely coupled multiprocessors are programmed via message passing, meaning you have 2 threads that you wrote, and they have to explicitly send and receive data. They have explicit calls that they make, send and receive for communication. They don't use load stores, basically, on a shared memory location, for example. Whereas here, tightly coupled multiprocessors, programming model is very similar to uniprocessors. Uniprocessors, we do load stores. We keep doing load stores to communicate between the different threads, right? A thread can update a memory address and another thread is going to read. So it sounds quite intuitive, right? And so except operations on shared data require some synchronization, right? Because if you don't synchronize, you may get the wrong values. And we're going to talk about how to support synchronization in hardware in a little bit. So, okay. So usually these are programmed using load stores. I say usually because it doesn't have to, right? Your programming model can be completely separate from how your hardware is built. Your hardware can support shared memory. You can say at the programming model, no, programmer, you're not going to use shared memory. You're going to use message passing. And that's perfectly fine, right? If that's what you want to do in the design of your system, you can have a message passing program executing on a shared memory hardware. Keep this in mind. What we're discussing here is the hardware execution model. But the programming model can be totally orthogonal. You can have a shared global memory address space multiprocessor. You can program it using single instruction stream. And you can use thread level speculation so that you can actually utilize the underlying hardware, right? So this is, I think, important. We're talking about types of hardware, but programming model can be completely orthogonal. Similarly, you may have a multi-computer network. You can say, programmer, I'm going to give you the illusion that this multi-computer network that has no hardware-based shared memory space actually will have completely shared memory space from your perspective. Meaning you're going to enable a programming model to the programmer such that the programmer is going to write threads, and these threads are going to operate on loads and stores. And underneath, the system and the hardware will convert them to explicit send and receive calls. Makes sense. It's possible, right? There's nothing that says you have to expose exactly what the hardware does to the program. That's why we have these abstraction layers. Why would you want to do that? Why would you want to take advantage of, well, maybe I'm biasing you already, but why would you want to turn a multi-computer network and make it look like a shared memory multiprocessor to the program? Anyone? Yes.
Maybe you want to run some legacy application that runs better in a cluster, for instance.
Exactly. Yeah, that's one perfectly good reason, right? You have some legacy application that's written in shared memory model. The hardware you built for some reason looks like a multi-computer network. Maybe you thought that it was easier to build that hardware. In fact, it's usually easier to build the top hardware if you want to scale to thousands, hundreds, thousands, and millions of nodes, let's say. Because you don't need to provide the hardware support for shared memory, right? Shared memory hardware support is very hard to scale. First of all, even your address bits need to scale, right? If you want to have an exabyte level memory address space, what was exabyte? It's 2 to the 60, right? You have to have 2 to the 60 bits basically. If you want to go into one order of magnitude, that's 70 bits. Well, are your addresses going to be 70 bits now? So this is the scalability problem, right? Whereas scaling, that is easier because you don't have shared memory space. Each memory space for a single processor is much smaller, maybe even 32 bits. So even that address bit scaling is easier. So there could be reasons why your hardware may be different from your programming model. And you could make the same argument over here, right? You say, okay, I have a shared memory hardware, but for some reason, I'm going to ask the programmer to program in message passing only. And I'm not going to give them even the primitives to do loads and stores. They cannot see the underlying loads and store-based hardware, basically. Why would you do that? What is one reason for doing that? There could be many reasons, of course, but yes.
Some people have argued that it is easier to write correct programs with message passing.
Exactly, and that was what I was thinking also. Potentially, it's usually well. Again, this is based on what we know, right? Or what maybe how we're educated potentially, but it may be easier to make mistakes when you're actually when you're actually programming and doing loads and stores to arbitrary locations in memory. If you forbid the programmer from doing that, maybe they have to think harder about when to communicate and what to communicate, right? They cannot just do an arbitrary store or load, which may lead to a bug. Right? In fact, some bugs may be happening because you're actually doing loads and stores and you don't have any explicit calls to communicate. So there could be multiple other reasons, of course, right? But that's one reason. So keep this in mind, basically. Even though we're not going to talk about the programming model and hardware distinction as much right now, these two things are completely independent. Okay, any questions? Yes.
So if I understood it correctly, the loosely coupled multiprocessors have no way of guaranteeing like synchronization between potential different threads. Like
Well, no, that's not true. Basically, the synchronization is done through these send and receive calls. So you have support for those send and receive calls. And maybe some other primitives, right? But there's no shared global memory address space. Meaning each processor has an address space on its own that no other processor can see. So whenever you do a load and store, you just see your own address space. And if you want to actually communicate a piece of value, you say, okay, I take this piece of value, I'm going to load it into my register, and I'm going to send it to processor 5. That's the synchronization and communication mechanisms.
also ensures that there's no like double access location, right?
Yes, from different processors, there's no concurrent access to the same location. That's correct. Yes. So everything is explicit. Yes.
So you said it might be beneficial to essentially abstract tightly coupled multiprocessors to look like loosely coupled processors to the programmer. But the question is, are there situations where that would cost performance, perhaps? Sort of like for example, like the concept of neural networks, right, are not best implemented on the hardware of von Neumann. They're probably best implemented on all these new accelerators we're making. So I guess, is there also, I guess, programming structures that would best be, I guess, done to exploit the, I guess, the tightly coupled multiprocessor architecture underneath with the direct.
Yeah, absolutely, absolutely. So basically, it's a trade-off. I mean, we didn't cover all of the trade-offs, but if you have a shared memory hardware, and if you program it using message passing, you may be leaving some performance on the table, right? Because the programmer is not going to optimize right now the loads and stores potentially, right? You can quickly communicate with loads and stores in the hardware, but the programmer is not exposed to it. Make sense? Yeah. Yeah, you can certainly be leaving performance on the table, but maybe the programming is more correct and less prone to bugs. Who knows? Yes.
I think this is just something interesting. There is some research that points towards that message passing isn't actually leading to more correct programs. I cannot cite it, but yeah, I think that's pretty interesting actually.
Yeah, doesn't you said does not. Yeah, well, I think it's hard to do research in this area. I would say I've seen both aspects and both arguments. Usually, it really depends on the program, problem, the type that you're solving, experience of the programmer, how they're educated, etc. So there are a lot of aspects that go into it. That's why I didn't want to make the claim that, and you also correctly said that according to some people, right? So it's not clear which one is less bug prone or more bug prone, because if you forget some send and receive calls, clearly you're going to be more bug prone on the top part, right? Potentially. So yeah, I think in general, I think of this as if some problems actually fit the send and receive much more easily. If you think about explicitly communicating events, for example, if you're doing some event-driven programming, perhaps that may be more fit over here. But if you're updating a database table, for example, that may be better fit over here, right? If you have a fundamentally shared data structure, it may be easier to update it using a shared load store type. But again, there are multiple factors that go into it. That's why it's hard to do research, I think, to answer that question very easily. Okay, so we spent a lot of time on the slide, but hopefully it was interesting. I mean, we don't have a parallel computer architecture course. This is the course that's related to it the most, but there are a lot of topics in parallel computer architecture actually that are quite interesting. And these are actually very fundamental topics. I mean, we can spend easily multiple lectures talking about programming models, execution models, how one maps to the other, and what are the trade-offs. And there are a lot of interesting things over there. But let's talk about tightly coupled multiprocessors. I'm going to ignore loosely coupled for a while. Well, part of the reason is tightly coupled multiprocessors are everywhere today. Multi-core is tightly coupled. Multithreading is tightly coupled. Basically, this is the dominant thing that we have. Yes, network-based multiprocessors are also there, but they're not the core currently. The core is really multi-core, which is tightly coupled today. That's how it is, right? You could like it or not like it, but that's how it is today. And there are many design issues in tightly coupled multiprocessor. These also have their counterparts in loosely coupled, but we're not going to talk about their counterparts. We're going to assume shared memory, hardware, and we're going to take a look at some of the design issues. Well, if you've taken a parallel programming course, how many people have taken this again? I think I've asked this question multiple times. So I think it was half and half or something like that. It's still half and half. Then you probably know that you need to synchronize between processes, right? And how to handle synchronization at the programming construct level, locks, atomic operations, barriers, etc., that we've been talking about, is something important. But again, we don't have time to go over that in detail. There's parallel programming course is the right place to think about it. If you had time, we would talk about this more also and how it interacts with hardware. We kind of did that in the last two lectures. We're going to talk about cache coherence. How do you ensure correct operation in the presence of private caches keeping the same memory address cached across different processors? And this is going to be important. And this is going to be especially important in shared memory processors. We're going to talk about memory consistency, ordering of all memory operations, which is what should the programmer expect the hardware to provide? And maybe we're going to see surprise in terms of expecting something from the hardware, because I think this is interesting and important, very fundamental. And these are scalability issues also, because if you really want to scale the number of cores to million, for example, or more, you need to support these in shared memory. Shared resource management, we talked a lot about that, right? And communication, well, hopefully we'll talk about interconnects. If not, I'll point you to lectures. And these are main issues, main design issues. They affect your performance, scalability, energy, everything, basically. And there's programming issues as well. I guess the first one could be also programming plus design, but okay. We talked about some of these programming issues. Load imbalance, for example. How do you partition a single task into multiple tasks? Clearly, that's important. This affects your performance immediately. Synchronization. How do you synchronize efficiently? How do you communicate between the tasks? And what kind of synchronization primitives you develop and use? Contention. Whenever you're contending for shared data or synchronization primitives, how do you avoid it as much as possible so that it doesn't happen? And how do you manage it when it happens? How do you maximize parallelism, maximally utilize your hardware? And how do you ensure correct operation while optimizing for performance? So this is going to be a key trade-off that we will look at, correct operation and performance. But before I move on, I will give you an aside also, because we've talked about multi-threading, right? And there are different types of multi-threading also. Clearly, you can have a single core and you can run multiple threads on it as well, concurrently, hardware threads. For example, there are three types of multi-threading, one of which we discussed in digital design and computer architecture, fine-grained. Basically, every cycle, the processor switches to a different thread. So you execute a different, an instruction from a different thread every cycle. And then you're overlapping, you're exploiting parallelism, instruction level parallelism across different threads in this case, and you're filling your pipeline with different threads. And this is not the most aggressive form of multi-threading. You can combine it. Simultaneous multi-threading is, you can basically have multiple threads. And even in a given cycle, you may be selecting instructions from different threads at the same time so that they can go to different execution units. So this is simultaneous, basically. At the same time, you're executing instructions from different threads. This improves execution unit utilization. So, for example, you design a processor with 6 ALUs. One single thread may not be keeping 6 ALUs busy, but if you have 6 threads, each of them may be executing a single arithmetic instruction at a given time. And if you can run them in parallel simultaneously, you get parallels. Yes.
Something I've been wondering about recently, again, since we've discussed a lot about that most of the effort in the processor goes towards data movement and not the processing itself, actually. Why are we worried about this simultaneous multi-threading then, if we could just duplicate the processing element without much cost?
I see. Well, it's still cost, right? So let me try to understand your argument. Basically, your argument is that let it be not utilized, the processing element. Is that correct?
Yeah, I mean, we've argued multiple times now that the computation itself is not that expensive in hardware. So we could just duplicate it, I guess.
Yeah, well, okay. So there are two answers that I would say. Not all problems are memory bound in the end. Yes, a good chunk of the problems are memory bound, but when you're compute bound, you're really compute bound. You don't want to waste your hardware. The second is, it's still waste, right? An ALU is still waste. Yes, it doesn't occupy as much area depending on what you do in the ALU. It doesn't consume as much energy because you can clock gate it, etc. But you're still wasting area basically. And that's not a good thing necessarily. And maybe the third argument is that once you solve the memory problem, you're hopefully bottlenecked by your ALUs in the end, right? But I think your point is still needs to be considered. But in the end, we don't want to waste, in my opinion. And simultaneous multithreading allows you not to waste. This is also called hyperthreading by Intel, basically. Intel changed the name to hyperthreading so that they can market basically better. And the first one I will discuss last is the coarse-grained multithreading. Basically, it's a quantum-based. There are two ways of thinking about it. You basically divide the time into quantums and give some number of cycles to each thread. Every quantum you switch to some other thread. This is more coarser-grained. Or you can switch based on event. So one thread gets a cache miss, for example. You switch to some other thread so that you don't wait or you utilize the resources better. Right? And clearly, these can be employed together. You can combine all of these approaches. These are conceptually combinable, and in implementation-wise are combinable also. Okay, so we covered fine-grained multithreading in digital design and computer architecture, and this is a lecture. And normally we could have actually a lot of lectures on multithreading. These are some lectures from 10 years ago, if you're interested in nostalgia. And I look younger over there, as you can see. But we're not going to cover multithreading more, but there are a lot of interesting issues over here. Like we used to discuss hyperthreading. And also redundant execution using multithreading and multiprocessing. That's also very interesting, but unfortunately we don't have time right now. Okay, so you can, if you're interested, you can actually look at these lectures. But let's now talk about some issues with multiprocessors. I'm running a little bit late, but it's good that we're having good discussion. I want to talk about some fundamental issues. And we're going to play some games, let's say, or solve some puzzles. Well, we discussed limits of parallel speedup. I'm going to go back to that in the end, Amdahl's law. But let's play this game or solve this puzzle. So this is a polynomial equation, right? It's written in some odd fashion over here, but essentially, AI is a constant, X is some variable, and this is the equation that you want to compute. And you're given inputs, X, as well as each AI, A0 through A4. So what this equation is doing is multiplying A4 with X to the power of 4, adding to it A3 times X to the power of 3, ... You can get the rest. Right? So we're going to compute the parallel speedup that we get under some assumptions. And these are the assumptions. Assume each operation, multiplication, addition, there are two operations in this case, is one cycle. There's no communication cost between different processors that you may want to parallelize it. And each operation can be executed in a different process. So this is an ideal scenario, if you will, for parallelization. No communication cost. That sounds great. Everything is one cycle. That also sounds great. And you can perfectly parallelize it potentially, but we're going to be limited by dependencies clearly, right? So the question is, how fast is this with a single processor? That should be easy, hopefully. You have a single processor and you're going to do some number of operations. Assume no pipelining or concurrent execution of instructions. Basically, every instruction, every operation, multiplication or addition takes one cycle. That's it. Ignore pipelining, etc. They're all additional, let's say, overheads. What we're going to look at is very fundamental. Okay, anybody? Any guesses for the first question? You can use paper and pencil if you want, or if you're much better than me, you can use your head directly. Okay, there are 3 guesses. I'm going to take, how should we start? 4 guesses. Why did you start? 12 cycles. Okay, I'm not going to ask you how you computed, otherwise we will spend the entire lecture here, but 12 is one. Okay, maybe I'm not going to write. 17? Okay. 11?
14?
14? Are you going to revise your answer? No, not yet. Okay. You're going to not execute the program. Okay. 8.
11, 12 seems. Yeah.
11, 12 seems reasonable. You're approximate, basically. Why not compute this approximately? That would make approximate computing people very happy, but not necessarily your program correct. Okay, I mean, even with a single program, now we're getting these widely varying answers, right? I thought this was going to be very, let's say, consistent. So I think the lowest number I heard was 8, and highest number I heard was 17. I'm not going to answer right now what is the correct one, but let's see. I think 8 is closer. But I think the common answer was 11. Okay, how fast is it with 3 processors? This is harder to do, probably, a little bit. You may need to actually use your hands. But you guys are much smarter than me, so maybe you don't need it. I need my hands here. I cannot do this in my head. Any answers? I'll give you some time. Okay, we're getting some answers now. Let me do something here. Okay, go ahead.
I'll be approximate again and say 5 cycles.
5 cycles, okay.
Yeah, 5.
Okay. 5, 5. Now we are getting more consistency. You guys are better at parallelization than just single thread. Yes. Anybody? I thought I saw another hand, but maybe they decided not to. Okay, 5 seems to be the consensus answer among a small number of people, let's say. Okay, let's do this with 3 processors first. I think 5 is the right answer. Well, of course, you can do it with more cycles, right? But I think 5 is the minimum answer. And this is how I would go about doing this, basically. And I'm not going to go through this again. You can study it. But this is x squared, and then a4 times x squared, and then, yeah, and then you do the addition over here. Okay, and you can study this basically. You basically create a data flow graph. You have all the nodes, right? You create a data flow graph, and you figure out what can be executed without any dependencies. What has all the things available, and then you basically compute. Is this how you do it? Okay. There are multiple ways of to go about doing it, but this is the smallest number. If it's actually wrong, and if you get 4, let me know. But I don't see how it's possible, because this is the longest dependency chain you have over here. You can of course make it longer, right? Okay, so that's 5 cycles. So speed up with 3 processors, I would say 11 is the right answer for a single one. Why? Well, you have 11 operations over here, right? Yes.
If you optimize this with Horn.
Okay, yeah, well, don't take away my thunder. Yes, basically, 11 is not the right answer, basically. But 11 is the easy answer, right? Okay. Okay, somehow I missed this one, basically. T1 is actually equal to 11 cycles. Why? Because you have 11 operations. You just come up with a data flow graph based on just what you're given without optimizing it in some way. And that's 11 operations, and you get 11 cycles because you have a single processor, right? And no, yeah. And this is the 3 processor version, 5 cycles. Speed up is 2.2. Right? And probably many of you actually would get this answer if we collect your answers, because you said 11, 12, 11, and then divide by 5 is 2.2. But you need to revisit the single processor algorithm, right? You can actually have a much better single processor algorithm and optimize this with Horner's method, as you said. Read this paper from 1819, or remember your high school mathematics, if you will. Do people still teach this in high school? Horner's method, how to factorize. Really? Yeah, some people say yes, some people say no. Maybe people don't remember, or how did you know about it? Okay, interesting. What course was it? Okay. Well, when I went to high school, it was taught in high school. So you know about Horner's method, but I don't know how high schools are these days. And it depends on the country and place, of course, right? But basically, Horner came up with a way of factorizing such polynomials, and that's basically what it is. You can read formally what it is about, but you basically take out the variable, and progressively you multiply it. And this is how you would optimize it. And this clearly reduces the number of operations you have over here, right? So instead of 11 operations over here, now you have 8 operations. And you can do them in 8 cycles, as you can see. So speed up with 3 processors is really now down to 1.6. You have 3 processors and you're not getting 3x speed up. Before you were not getting 3x speed up, you were getting 2.2x. Now, if you optimize your single thread program, you realize that your processors are actually not giving you as much speed up as you would want, perhaps, right? 60%. And you're dedicating 3 processors. Okay, so basically we've discussed this briefly, but it's important to be very fair and careful about comparisons when you talk about speed up. I could easily show you an example with superlinear speed up. Basically, we've seen this sort of graph before, right? Number of processors on the x-axis, number of the parallel speed up compared to a single processor on the y-axis. And I said usually you get a typical success that looks like this, and we've seen these equations, we've seen these examples, accelerated critical sections, for example. If you get linear speed up, you're really lucky, because that means that you have no sequential bottleneck and no bottlenecks in the parallel portion. Now, if you get superlinear speed up, you should probably question what you're doing. And any speed up you should question, basically. So can speed up be greater than P with P processing elements? And the answer is yes, absolutely. And there are 2 major reasons for it. Actually, I alluded to these reasons. One is unfair comparisons. Right? If you're unfair, meaning you have a best parallel algorithm, you optimize this parallel processor, you're very excited about it, and you want to show this huge parallel computation to the world and sell your processor also. You compare it to wimpy serial algorithm that you didn't optimize. Yes, the speed up is real, but it's unfair, right? Someone can say, oh, okay, I have this much better serial algorithm and your speed up is not superlinear anymore. And whenever you see the superlinear speed up, it's sometimes because of this. And sometimes it's because you're adding more resources to the system. And now that we're going back to memory, basically, and cache and memory or storage effects, basically. This picture assumes that the resources that you're adding is just processors, right? Computation. But more processors can come with more cache and memory. And as a result, you may get fewer misses in the cache and memory. You may be going off chip much less, for example. As a result, you may actually sometimes get superlinear speed up effects, right? For example, you have 1 processor, I don't know, 1 megabyte cache. You have 4 processors, 4 megabyte cache, and your data set is 3 megabytes, regardless of the number of threads. In the second case, your data set completely fits in the cache. You don't go to memory. As a result, you may get a superlinear speed up, right? And that's exactly the reason why this may actually happen. Clearly, this is, you'd say this is not unfair necessarily. Yes, in a sense, it's not unfair, but maybe you're not marketing nicely, let's say, or maybe you're not reporting things nicely, because your speed up is not just coming from parallelization. It's coming from cache and memory effects in this particular case. And if you come up with other reasons, let me know. But I think these are the 2 fundamental reasons. Maybe we should say not just cache and memory effects, but other additional resources that is affecting your performance rate. Usually it's cache and memory, though. Okay, it could be network bandwidth in some cases, of course. Okay, so there are 3 traditional metrics that we evaluate processors with. I'm going to go through this relatively quickly, but these are important for understanding the efficiency and redundancy and utilization. Well, those are the metrics. Those are what the metrics are called. But basically, let's take a look at these metrics. Assume all P processors are tied up for parallel computation. You have some task, you parallelize it, and you dedicate all P processors to your task. Now we're going to define these metrics. Utilization is how much processing capability is actually used. You have some processing capability, what fraction of it are you utilizing? And this is basically computed this way. You basically are tying up P processors for some amount of time. How many operations are actually executing? We're going to compute this based on the example that we see. How much of that time is actually really utilized time and not time that's wasted, basically? redundancy is how much extra work is done with parallel processing. And usually, when you go from single, let's say single thread to parallel threads, you're adding more work. And you will see this example. Even in our example, we're going to be adding more work, additional work. And we assume no communication, even no additional communication, right? Additional communication is work, for example, but we're assuming 0. But you may need to replicate instructions, replicate data, etc. And redundancy is like this, basically. Number of operations in the parallel version divided by number of operations in best single processor algorithm version. And efficiency is essentially how efficient you are, right? Time with one processor divided by processors times time with preprocessors. I'm going to give you the example of it. And efficiency can be computed as utilization divided by redundancy also. Let's take a look at utilization. In our example earlier, let me go back to the parallel version very quickly. It looks like this, basically. You're basically tying up 3 processors for 5 time units, right? Because there's 5 time steps. But not all of those slots are utilized. Basically, we have 3 processors, 5 time units. Some processors are not doing very well in terms of utilizing their slots. And this is an example of load imbalance. Basically, utilization is very much affected by load imbalance. Your load is imbalanced across processors. And you can see that your utilization is 66% in this case, right? 2/3. And you can see the calculations over here. Okay, that's utilization. Redundancy is how much extra work is done due to multiprocessing. Basically, operations with key processors is 10. So if you count these, this is 10, 5, 3, 2, 10. Whereas we said you need only 8 operations with a single processor. So that's redundancy is always greater than equal to 1 because you need additional operations in general. And we're not even taking into account communication or replication of data. And efficiency is basically how much resource you use compared to how much resource you can get away with, let's say. So in efficiency, ideally you would in the single processor version, you tie up one processor for some time units with the best algorithm for the single processor. When the parallel version, you're tying up P processors for 5 time units in this example, which is how much time do you need to execute your parallel program? And efficiency is 8 divided by 15, basically, in this particular case. So it's almost 50%, let's say. Okay. Any questions on this? This is just interesting things, let's say. But you can compute all of this for any program, basically. Looks like it's snowing, so we can stay here until breakfast, maybe. Okay, let me go through Amdahl's law and caveats of parallelism relatively quickly, and then we're going to take a break and transition to memory consistency. But basically, what we're talking about is really about caveats of parallelism. All of this efficiency, utilization, redundancy. It's all about performance and how well you're taking advantage of your processors, right? Basically, you remember this is a superlinear speed up example that I gave over here. This is your reality. Why do you get the reality? Because of Amdahl's law, basically. Or Amdahl's law generalized to parallel bottlenecks as well. Basically, you get diminishing returns, right? You have a parallelizable fraction of the program, and ideally, you would parallelize it perfectly. And you have a non-parallelizable part that limits your speed up, right? And we've seen examples of this, so I'm going to go through this relatively quickly. You know about Amdahl's law. And Amdahl's law is very strong, though, as we discussed. These are the curves that you would get, basically. Adding more and more processors gives less and less benefits, basically. So if your parallel fraction is 90%, the curve looks like this. So adding more and more processors, your curve is kind of flat, right? And that's true for all of your parallel fractions that I show over here, unless it's 1. If it's 1, then you get, let's say, equal benefit from each processor that you keep adding, right? But that's not the case if your parallel fraction is smaller than 1. Okay, and the benefit is small until alpha is equal to or very close to 1, which is a parallelizable fraction. I used F in the past, but I guess I don't want to change my figures over here, which are relatively old. But you get the idea, right? Okay, so I think these two things are really interesting, right? Adding more and more processors, unless your alpha is 1, gives you less and less benefit. That's the diminishing returns part, right? That's what the shape of the curve shows. And looked another way, alpha on the x-axis and speed up on the y-axis, the benefit is very small unless alpha is very close to 1. And that's Amdahl's law we've seen. And this is not even taking into account the parallel portions bottlenecks that we discussed earlier. And you know those really well. Again, if you come up with a new part over here, I ask this question every semester, but I never get a new answer. So maybe these are really fundamental. Synchronization, load imbalance, and resource sharing. And okay, this is real data, Excel sheet data, basically. Those were my hand-drawn equations, but if you actually put this in Excel, this is your parallel fraction on the x-axis, and these are the results that you get. With n equals 1,000, you get benefits only around here, basically, if your parallel fraction is very high. Until here, well, it's not that much. Well, you could argue that, okay, 10x is a lot, so maybe this region should be also considered. Fine. But you're throwing 1,000 processors to get that 10x right, or maybe 100 processors in the red curve. Okay, so why do we have the sequential bottleneck? We discussed this, right? All parallel machines have the sequential bottleneck, so don't forget this. Some people have argued like Amdahl's law doesn't exist, made these really bold claims, etc. I don't know why. These are actual professors. Very interesting. It exists. If you cannot parallelize perfectly, you're back to the serial part, basically. So basically, you can have non-parallelizable operations on data, non-parallelizable loops, for example. Examples, there are other causes. Single thread prepares data and spawns tasks. So that even the task preparation of a single thread is part of your Amdahl's law. You have a serial thread that's trying to distribute tasks to different threads, right? Well, do it quickly. If you cannot do it quickly, if you spend 5% of the time, you just gotten rid of, you basically made your parallel fraction at most 95%. So this is very fundamental. If someone claims Amdahl's law doesn't exist, well, I don't know what Amdahl thinks about it. Well, the data certainly doesn't say that. Okay, I mean, these are examples. This is actually the task distribution that I mentioned. So these are different. This is a program. Basically, it creates, it's a dynamic tasking program, let's say. You spawn threads, and you're solving some problem. This is usually how a dynamic tasking program works in general. Basically, you create some subproblems. Let's say you're exploring a maze in a breadth-first manner. You're searching, you're coming from here to here, and you have some bottlenecks. And with threads, you're exploring the space, and you want to go from here to here. And as a thread progresses from one location to another, it creates new tasks to explore the space, let's say. I mean, that's one example, right? So basically, a thread comes, it picks a subproblem, it tries to solve the subproblem, and if the problem is solved, meaning the exit of the maze is reached, then you're done. If not solved, you create new subproblems for other threads to solve, basically. And whenever you create new subproblems, you insert them into a task queue. And this task queue is queried by every single thread in this critical section 1, as you can see, so that they can get a task to solve. Basically, it's a dynamic tasking program that keeps generating new tasks so that you can solve them. Puzzles are, for example, different sort of puzzles could be solved this way, but I like the maze example also. Clearly, you can have a single thread trying to solve the maze, but if your maze is huge, you may not be able to get very high performance to explore the huge structure of the maze. Now think about a 3-dimensional maze, or maybe 4-dimensional maze. Then it becomes even more difficult to explore it with a single thread, right? Okay, but you can see that there are critical sections over here. Those are parallel bottlenecks. There are parallel portions, which is D1 over here, but they're completely serial portions, which is the initialization as well as the end over here. And if those take a significant amount of time, then Amdahl's law is there. Again, and this is one example of the execution of this program. So A and E, if they take too long, it doesn't matter what you do over here. You're bottlenecked by A and E. And within what you have over here, you're still bottlenecked by the parallel portions as we discussed. Okay, so let me just a reminder, bottlenecks in parallel portions, synchronization, operations manipulating shared data cannot be parallelized. This can be also called communication. I don't like calling it communication as much because you're really synchronizing. Communication may happen. Well, communication implies some sort of synchronization, no question about that. But synchronization is a better word for it, I would say. But you could also say communication type of bottlenecks over here. And tasks may need values from each other, basically. And this causes thread serialization when shared data is contended, as we have seen in earlier lectures. Load imbalance, parallel tasks may have different lengths. due to imperfect parallelization or microarchitectural effects. We saw example of imperfect parallelization, but it could be due to microarchitectural effects also, right? One processor may be faster, but the other processor may be smaller, slower. That could lead to load imbalance for various reasons. One processor may have good caching capability, and another processor may not have good caching capability for some reason. The prefetcher may run faster. So there may be many microarchitectural effects that actually affect the load imbalance as well. And this reduces speed up in the parallel portion clearly. And resource contention, we've seen this many, many times, right? Parallel tests can share hardware resources and delay each other. And clearly replicating resources is expensive. That's why we have resource contention in the end. And this leads to additional latency that's not present when each task runs alone, as we have also discussed earlier. So another view of bottlenecks in a parallel portion is, well, we've discussed this actually. Threads synchronize with each other. Some threads can be on the critical path of execution, some threads are not. And even within a thread, some code segments may be on the critical path of execution and some are not. So I think we've gone over this, so I'm going to go through this relatively quickly because we're already running late. Otherwise, we might have some more discussion on these, but hopefully you guys are all very comfortable with critical sections, barriers, and stages of pipeline programs. These are some examples of synchronization methods that could lead to these bottlenecks in the parallel portion. Okay, so since we've covered that. So again, difficulty in parallel programming. Parallel programming is not difficult if the parallelism is natural, I would say. Some people say embarrassingly parallel applications, for example. Graphics is supposed to be one of them. Physical simulation, multimedia. As long as threads are not interacting with each other, it's relatively easy to parallelize. The difficulty happens when threads actually start interacting with each other, either semantically or in hardware, in resource contention, for example, right? As a result, parallel programming becomes difficult because of those interactions, right? The difficulty is in getting parallel programs to work correctly, first of all. We've discussed that. We're going to discuss more. And optimizing performance in the presence of bottlenecks. And much of parallel computer architecture is really about handling these, designing machines that can overcome the sequential and parallel bottlenecks to achieve higher performance and efficiency, while, let's say, keeping the programmer sane, or making the programmer's job easier in writing correct and high performance parallel programs. And these are really key, basically. How do you design machines that are high performance and efficient? How do you make programmer's job as easy as possible? If you don't do the first one, then it doesn't matter what the programmer does, perhaps. If you don't do the second one, then again, it doesn't matter what you do over here, perhaps. Right? And there are examples of this a lot in systems. For example, IBM designed the cell processor. I don't know how many people are familiar with cell processor. This used to be in Sony PlayStations, for example. And it was the first heterogeneous multi-core processor, actually. They had a control processor, and they called it, I think, primary processing element. And then they had synergistic processing elements, 8 processors. These 8 processors, it was actually quite good. It could actually execute really fast, except the programmer needed to do a lot. For example, they didn't have cache coherence in this machine. So the programmer needed to explicitly manage the caches. And there were some other idiosyncrasies, basically. They didn't have easy mechanisms to manage the different heterogeneous processors, etc. And the compiler was not very good at helping the programmer, let's say. Actually, there was a lot of research on cell compiler. It was actually quite good, but still not good because the programmer didn't have support. Their job was not easy. And again, that project was abandoned. There may be other examples that we can discuss later when we talk about, let's say, memory ordering, perhaps, and cache coherence. But I think you need to do both, basically, in parallel computer architecture. You cannot say, okay, I have this great hardware, programmer, do your, whatever you do, just program it. That's not a recipe for success. There may be some programmers who can do it, but most of the world are not that sort of programmers. And clearly, if you don't design machines that are good, then they're not going to be used. Okay, we've already seen examples of this actually with accelerated critical sections, bottleneck identification, scheduling, utility-based acceleration, and data marshalling. These are all trying to solve the problem of how do we actually reduce the overhead of these parallel and serial bottlenecks while also making it easy for the programmer to program. These don't ask a lot from the programmer, except following disciplined, let's say, parallel programming primitives, right? Okay, that brings me to the end of the first part, which is good because we have exactly 16 minutes until 3. So maybe we should take the traditional 16-minute break today. unless there's a burning question. Okay, so let's take a 16-minute break, and we're going to talk about memory ordering in the next part of the lecture. Oh, oh, thanks a lot, Jason. And hopefully it'll be useful. Oh. Sure.
So there was any significant difference between many core and multi-core today, or is it like just?
Well, initially, people, yeah, that's a good question. When do you decide it's many and not multi anymore, right?
Is it even relevant today?
I don't think it's as relevant today, but I think when people think about many core today, it's like hundreds of cores as opposed to tens of cores. In the past, I think, because we already had tens of cores, right? Yeah, that's what I would say. I don't think it's as relevant. Partly because people expected core counts to scale as fast as transistor counts, and that didn't happen, right? Cache is scaled much faster than core count for obvious reasons, like we discussed, right? I don't think it's as big of a debate today, I would say. And part of the many core benefits were actually stolen, let's say, from GPUs, right? GPUs actually took a lot of the potential benefits many core could have given, right? Yeah.
So, yeah, just a quick tangential. So there
Sure.
was this really famous company from MIT called Tylera.
Yeah.
By this.
Yeah, they still exist. Huh?
I mean, they just got sold and it's just a patent.
Yeah, maybe that's right. That's right. Yeah, yeah. But their goal was to do this many core, very simple processors, mainly for embedded applications.
But I
Yeah.
couldn't understand why they failed. I mean, it was such a promising paradigm, and today's applications really needed. And then you have all these cloud providers which are running these just huge farms which need these kind of just simple but a large number of cores. And
Yeah, well, those were actually very simple cores. So I don't think they would be very useful for the purpose that you mentioned. So I would say that was never meant to be a really general purpose system, unless you could actually really parallelize your program extremely high. But even then, the single thread execution was very slow in those cores. That was more like, like large scale embedded processing, for example, or signal processing. I think they would do quite well in those tasks potentially. Yeah. I think that's probably part of the reason why it didn't
it didn't
succeed.
just
Yeah.
take off.
Yeah, but it was promising for sure. Yeah. I mean, Larrabee didn't take off. Also, Intel Larrabee is another example, right? For I would say many core when multi-core was coming up, but there were programming issues, clearly software issues. Okay, sure. That's not what I'm sharing. I assume the video is visible. People on Zoom? Okay.
Yeah.
Yes, that's good. Okay. Now we're going to continue with one example issue in shared memory multiprocessing. I mean, this issue also exists in message passing too, but shared memory multiprocessing makes it much more interesting, let's say, which is the issue of memory ordering. And we've seen this issue in digital design and computer architecture also. This ordering of operations actually is important so that the programmer can be sane, right? There's a contract between the programmer and hardware in von Neumann architectures, which is you don't execute another instruction before you finish the previous one that is written by the programmer, right? And we're going to see a similar contract needs to be developed in multiprocessors or MIMD processors as well, with some examples. This is also called memory consistency. It's an interesting topic for sure. Okay, so we've covered this just in the previous lecture. Basically, much of parallel computer architecture is about designing machines that overcome the sequential and pair bottlenecks to achieve higher performance and efficiency, and while making the programmer's job easier and writing correct and high performance parallel programs. So we're going to talk about this one. And we're going to especially talk about correct, and we're going to talk about its implications in high performance, and how do you achieve both correct and high performance at the same time, while keeping programmers sane, let's say. Before I go into it, we've kind of discussed this, but performance and correctness are, again, two of those metrics that are fundamentally at odds with each other. I would posit that, and there are many examples of this case. Basically, you can always improve performance at the expense of correctness, right? I mean, the easiest one is don't execute your program. Your performance is, let's say, infinite in that case, right? It takes 0 time, and clearly you don't get a correct answer. That's kind of perhaps not an interesting example, but it's a real example of the extreme end of the spectrum. Right? Or forget some critical lock in your program, or say, oh, okay, I'm not going to lock this because it's high performance, and hope that it's not going to affect your correctness, right? You could do that, sure. But the effect may not be what you want in terms of the result of the program. You can design your architecture to ignore ordering of operations. You can basically say, I'm going to take this sequential single-threaded program and execute things in parallel. I'm not going to report the results to the software as the programmer intended the results to be reported. Basically, ignore the semantic order of operations of the program. Yes, you can do that. You will get high performance. And people have done this actually. IBM 36091, one of the earliest out-of-order execution machines that implemented Thomas Sowell's algorithm. In its floating point units, what they did was they actually implemented Thomas Sowell's algorithm, executed instructions out of order, but they didn't have a mechanism to reorder those instructions like we discussed in digital design and computer architecture. So they actually reported the results out of order completely, even though the programmer had a single-threaded sequential program where each instruction should have been executed in the order that's written by the programmer. And what happened? They got good performance, but the machine did not become successful because of this reason, basically. Nobody used this. Well, people tried to use it, of course, but because they couldn't debug the machine, because they couldn't get imprecise exceptions running on the machine, IBM basically discontinued that line of out-of-order execution. In fact, there's an interesting story. When people wanted to build this machine, they had to get clearance from I think, the highest levels of IBM. IBM executives had to say, okay, you can do this. And they said it reluctantly. That was maybe a bad thing to do. It was great for research because this was the first machine that implemented Thomas Sowell's algorithm, and it enabled later research afterwards. But from a product perspective, it was not great success because programmers couldn't use it. So that's an example. That's a real example of performance correctness trade-off not making a machine work. And we will see examples of this fundamental support in multiprocessor operation now. That's a single processor, right? By the way, IBM 36091 was not the first out-of-order execution machine. It was a smaller company, Control Data Corporation 6600, that actually built the first out-of-order execution machine. It was one of the earliest supercomputers that was competing with IBM. And one of the reasons they were able to get this permission to break the correctness was because IBM people were furious that this small company beat them to actually get a supercomputer faster than IBM could build, right? How is it possible? And then they went into this performance correctness trade-off, if you will, and they were not very successful in the end. Okay, but I mean, over time, they developed very, very interesting things in IBM 360, of course, but this is one aspect of it. Okay, so we're going to talk about memory ordering and consistency in MIMD machines, and then we're going to talk about cache coherence. Cache coherence is another example where you can run into performance versus correctness issues, right? Or you can trade these off. But I would argue that these are not real trade-offs. So if you actually are breaking some contract, then you're probably making your machine unusable to a fraction of your users, and it may be a very large fraction of your users. But there are cases there when there's a real trade-off between performance and correctness. And this is when the application can actually tolerate it. And we've seen examples of this, right? When the application or user can tolerate the resultant errors, then you can actually exploit this trade-off intelligently. And clearly, these are not intelligent ways of exploiting this trade-off. It may work in approximate programs, right? And we've discussed examples of this, right? Remember heterogeneous reliability memory. Remember Eden, where you would actually decide what is the tolerable bit error rate for different types of data in your neural network, and map those data to different portions of DRAM that can provide you that tolerable bit error rate. Right, that's an example. That's true for heterogeneous reliability memory also. And clearly, this is a real trade-off that can be exploitable if you know what you're doing, I think. But if you're breaking things, maybe that's not good, right? I think performance versus correctness trade-off is very similar to another trade-off that we examined, latency reliability trade-off. I think this is also very fundamental. You can always make things lower latency if you get rid of, if you basically, let's say, give up some reliability. It's very similar. Performance, latency, correctness, reliability, right? They're parallels to each other. Reliability is at the hardware component level. Correctness is at the program semantic level or hardware function level. So it's good to distinguish between them in a sense. And we've seen examples of the latency reliability trade-off also, low latency memory, when we covered, for example, random number generation, physical unclonable functions. We're exploiting the latency reliability trade-off. And hopefully you remember the random number generation. We'll have another lecture on the topic that we did not cover, Quark TRNG, hopefully later. But this is just to jog your memory. Okay. Now let's jump into memory ordering in multiprocessors. I mean, I'm giving you this because you can run into similar trade-offs in memory ordering also, especially if you're running approximate applications. But if you are not running approximate applications, you don't want to run into this performance correctness trade-off in general. You do want to preserve correctness, I would argue. Otherwise, your machine may become unusable. I mean, even if it's not programmable, your machine may be unusable, right? I've given you the example of IBM Cell, for example. There's no correctness problem over there. It's just a difficulty of programming problem. Even then, people didn't want to use it. Okay, so as I said, the Lamport's paper, the seminal paper, is required. And I'm going to talk about actually these two papers that are actually quite fundamental also, Kuroshkar-Chorlu's papers. But let's first distinguish between the topic of this lecture and tomorrow's lecture, memory consistency versus cache coherence, because sometimes people confuse these. Even though they have some relation, they're completely different concepts. Consistency is really about ordering of all memory operations that are generated by different processes to different memory locations. Basically, this is all operations, the set of all operations from all processes. It's also called the global ordering, let's say, global ordering of accesses to all memory locations. How should different processors see the global order of operations from all processes? Should it be exactly the same? Are some differences allowable? Does it really matter? We'll ask that question also, right? Coherence, on the other hand, is completely different. It's about ordering of operations from different processors to a single memory location. It could be a single word, single cache block, single page potentially, right? So there are different granularities of coherence, of course, but it's about the same memory location in the end, given some granularity. And I would argue that this is called local ordering of accesses to each cache block, for example. Make sense? Okay, we're going to see why it's important in coherence. Coherence is about basically, you have multiple caches in your system. One of them has cached the data. Another processor is updating that location that's cached? How do you keep that data coherent so that nobody gets the wrong value or stale value? Consistency is nothing about that, basically. Consistency is going to be something different, as we will discuss. Yes?
Why are we worried? I'm not sure I understand the first definition.
Yeah, you'll see, hopefully.
If there are two different memory locations, we don't care, right?
Well, we will maybe. Maybe I'll ask you the question a little bit. Maybe we don't care. Yeah, that's why I said, why do we even care, right? Yeah. Okay, let's keep going. Maybe you will find a flaw in my argument that you will argue that you won't care still. Okay, but we will hopefully see an example where we will care. And this is going back to much of parallel computer architecture is about overcoming the bottlenecks and making the programmer's job easier. And we're going to look at both easier and enabling correctness as well as high performance in both today's and tomorrow's lectures. So let's talk about ordering of operations fundamentally, right? You have some operations, A, B, C, D. In what order? The question is basically, the broader question is, in what order should the hardware execute and report the results of these operations? Right? That's a very general question. And in the end, who determines this, right? In the end, it's really a contract between the programmer and the microarchitect, as specified by the ISA. The ISA says something, and everybody expects that contract to be obeyed. Otherwise, you may have a machine that's completely not programmable because you're expecting something, and you do that thing that you're expecting, but the result you get is not implemented by, not correct because the hardware doesn't implement what you expect, right? So this has to be, there has to be a contract. There's no other way of solving this problem, I would argue. And clearly that contract exists in von Neumann model. Von Neumann model clearly says there is a sequential order of operations, and that's it. Don't break this contract. You can break it underneath however you want, do whatever you want, but don't break it when you report the results to the programmer or the software or the user. Right? So why is this important? Because preserving an expected, or more accurately, agreed upon. And agreed upon really sets the expectation, right? You agree upon something, or somebody dictates it to you. Intel says, this is my order. Whatever you do it that way, right? You're forced to agree on that because you're using their processor, right? And that becomes an expectation after that point. And that expectation order simplifies programmer's life. Programmer learns to deal with it, basically, unless it's really extremely cumbersome to deal with it. Well, let's talk about the sequential execution, right? Von Neumann model. Why it has been so successful? Because it's very easy to reason about, right? You know what's going to happen. You know how to debug your programs. You know when you set a breakpoint, that breakpoint is going to ensure that there's a precise state, right? Well, the machine is going to ensure that whenever you actually, whenever it actually stops at that breakpoint, all instructions before the breakpoint have been executed, and no instruction after the breakpoint have been executed. So you have a precise state. You know that order, and this is guaranteed by sequential execution and precise exception semantics. And this is a state recovery, exception handling, like we have discussed in the precise exceptions lecture in digital design and computer architecture. But preserving an expected order has a downside. Like any idea, it has upsides and downsides. Now, it usually makes the hardware designer's life difficult. Right? Hardware designer can easily say, oh, okay, I'm going to execute operations in parallel. Why should I bother reporting the results in serial as expected by the programmer? Well, you have to bother so that you can obey the contract, but if you bother, now your hardware becomes more complicated, right? And the design becomes more complex. And we discussed all of that in digital design and computer architecture. You have a reorder buffer to reorder the results. You cannot write the results into the reorder buffer in out of order, so you have to buffer them. You have a load store queue, the store instructions. You cannot execute a load instruction before you know the address of the stores, or you need to do prediction. And if you do prediction, you need to recover if you've done the wrong prediction. So all of this really complicates the machine because you're trying to preserve this order that is agreed upon between you and the programmer. Especially if the goal of the design, goal is to design a high performance processor, right? And we call the load store queues in out of order execution, right? And their complexity. This is actually the least scalable part of an out of order execution processor. How do you execute loads and stores? You need to ensure that you don't break the semantic order that's expected by the program, right? In the presence of out of order execution. Again, I will point you to lectures from last semester. Well, not last semester, digital design and computer architecture. So we're going to generalize this to multiprocessors today in a different way, of course. But let's talk about the memory ordering in a single process a little bit more. This is really specified by the von Neumann model. Von Neumann model has two properties: stored program execution, sequential processing, sequential order, basically. Hardware executes every operation, let's say, in the order specified by the sequential program, specifically memory operations, load store operations. Load store operations are just specific examples of any operation. Okay, so there's no question about this clearly. Out of order execution does not change the semantics. Hardware retires, or in other words, reports to the software the results of the load and store operations in the order specified by the sequential program. There's no surprises here again. So advantages, like we discussed, architectural state is precise within an execution. Whenever you run the program once, you know exactly where you are in the program. Right? If you stop and observe at any given point in time, there's a point in the program where all previous instructions are retired and no later instruction is retired. That's the precise state. This enables you to recover to that state, checkpoint that state, handle interrupts, exceptions, and also do breakpoints and debugging. Debugging is actually very important. Perhaps debugging is the most important thing over here. Because they're actually very interesting solutions that people have developed in some cases. If you want to restart, for example, a machine, you can dump the microarchitectural state to a location in memory completely, go to some other interrupt handler or switch in some other program, execute it, and you can dump back all of the microarchitectural state back into the machine from memory. So it can actually enable restartability without precise exceptions, precise state. But debugging, that's very difficult. How do you actually give the illusion to the programmer that this is the point you stop the program and exactly what you expect is happening without you actually obeying that? That's very difficult. That's where precise exceptions really matter, actually. And that's why IBM 3691 failed from that perspective. Okay, so basically architectural state is precise within an execution. That's good. When you run the program multiple times, architectural state is consistent across different runs of the program, basically. You run the program once, you run the program twice, you get the same result. Unless there's something that, some input that changes in that is dependent on time or something else, right? So basically it's easier to debug programs in this case because of this ordering. Of course, the disadvantage is what we discussed. Preserving order adds overhead, reduces performance, increases complexity, reduces scalability. Now you have hardware costs, power, inefficiency, etc. As we discussed in this lecture that's pointed over here, which is a precise exception lecture from digital design and computer architecture, and out of order execution lecture also. Okay, so that's single processor, von Neumann processor. What about a data flow processor? Data flow processor is perhaps exactly the opposite, right? A memory operation executes when its operands are ready. Remember, data flow is an instruction gets fetched and executed whenever its inputs are ready. So it's completely data flow based. And basically you keep track of the readiness of inputs and fetch and execute instructions based on that readiness. Whenever the data is ready, you execute. There's no program counter, which means that there's no single thread of control. Ordering specified completely by data dependencies. And two operations can be executed and retired in any order if they have no dependency. So it's all about dependencies here. The advantage is lots of parallelism, high performance. Disadvantage is no precise state or ordering semantics. Good luck debugging this, basically. So, and precise state is very hard to maintain because there's no specified order to begin with. How do you enforce a precise state? And as a result, this is very hard to debug. Yes?
Isn't the data flow fixed once you have written the program?
Could you say it again?
I mean, it might be wrong, but once you've written the program, the data flow is always fixed. So you can always predict what's going to happen at any point of time, assuming a fixed start time.
Assuming everything is fixed, latencies are fixed, inputs are fixed, etc. There's no dynamic change, basically. Everything is static. The problem happens when you have dynamic latencies.
Yeah, makes sense.
Then the ordering changes a lot.
Yeah.
Basically, an order can change across the runs of the same program also. Within the same program, while you're running a program, basically, it's very hard to debug because you don't have the notion of precise state. An order can change across the runs of the same program. This is very hard to debug. Okay, and people have tried to actually enforce memory ordering semantics on a data flow processor. I think these efforts are actually quite tough. And in the end, they eliminate a lot of the benefits of a data flow processor. They reduce a lot of parallelism, basically, if you enforce a ordering of memory operations. Okay, now we're talking about MIMD processors. That's the subject of this particular lecture, right? But the others are important to think about, right? How do you make a data flow processor work? Is interesting to think about clearly. And this is one of the reasons why data flow has not been very successful at the ISA level. In the microarchitecture level, everything is data flow today. Out-of-order execution is restricted data flow, right? The results are reported with the von Neumann model, of course, right? Sequential execution. But doing this at the ISA level is very difficult. Okay. So in memory ordering, in a MIMD processor, each processor's memory operations are in sequential order with respect to the thread that's running on the processor. We're basically assuming that each processor obeys the von Neumann model. That sounds good, right? Reasonable, because each processor is running a single thread of control. Multiple processors execute memory operations concurrently. Then the question becomes, how does the memory see the order of all operations from all processors? In other words, what's the ordering of operations across different processors? And maybe you're going to ask, why does this matter, right, again? So why does this matter, basically? Let's take a look. So ease of debugging. It's useful to have the same execution done at different times to have the same order of execution. You run the multi-thread program once, you get some order of operations. You run it again. If you get the same order of operations, debugging would be easy, right? Because let's say you have a bug in the program and you're trying to solve it. You couldn't solve it. You run the program again. Hopefully, the order of operations remains exactly the same so that you could actually replicate exactly what happened in the previous program. If you cannot, maybe you don't even hit the bug, right? But this doesn't happen. This is not the problem we're going to solve, unfortunately. This is a much tougher problem, I would say. Repeatability across executions requires some enforcing of the same order. So usually the approaches to this sort of thing is you record and replay, meaning you record what has happened in the previous execution in a debugging mode, of course, exactly the ordering of operations, which thread synchronized, which thread took which lock, or did what synchronization operation at what point in time, and you try to replicate the order in the replay version while you're debugging. Even then, it's a lot of overhead, basically, to keep track of all of this information. But this is not what we're going to solve. But you can see that this is a problem, right? If you don't keep the order the same across different runs, debugging is harder. And I assume many of you have done multi-threaded program debugging. You probably know how difficult it is to pinpoint these synchronization bugs, especially if you've done some kernel programming. Anybody? Or maybe you guys are too smart. So you run into issues? I assume, okay, I see a lot of heads nodding, so that's good. You're not alone. If this was there, your life would have been a lot easier. But this is still a topic of research, basically, and unfortunately, there are no huge breakthroughs, let's say. I mean, record and replay, actually. I think, for example, VMware has some solutions to record and replay using virtual machines. I think those are the most promising approaches, perhaps. Okay, that's ease of debugging. Correctness is going to be what we're concerned about, and then that is going to enable our concern on performance and overhead as well. So basically, the question is, can we have incorrect execution if the order of memory operations is different from the point of view of different processes? And if the answer to this question is no, then okay, that's good. We don't need to do anything else in the ISA, perhaps. But maybe the answer is going to be yes in this case. And then there's performance and overhead. If you enforce some strict sequential ordering for whatever reason, it can make life harder for the hardware designer in implementing techniques that enhance performance by reordering operations. Clearly, we know this, right? In single processors, that's true. We have out-of-order execution caches, and we'll see that this will become an issue. So let's tackle this correctness problem. Let's go into it a little bit more detail. When could order affect correctness, or this sort of order affect correctness? And basically, the key point is whenever you synchronize, right, between threads, if the threads are doing completely independent things, and they're never synchronizing, they're never communicating, this is never a problem, right? You can probably, that's the axiom that I will have. You can probably prove this easily. I'm not going to do that, but I'll take it as an axiom. But when you're protecting shared data, threads are interacting with each other, and this order may matter. So let's remember protecting shared data. Well, clearly, threads are not allowed to update shared data concurrently for correctness purposes. And accesses to shared data are encapsulated inside critical sections or protected via some synchronization constructs like what we have seen, examples of locks, semaphores, condition variables. You can keep adding to this clearly. And only one thread can execute a critical section at a given time. That's your invariant. If for some reason, something you do in hardware or software breaks this invariant, then you're going to run into correctness problems, right? Potentially. Because you may have two threads in the critical section, but you may get lucky that they don't update the same part of your data structure that you're protecting potentially. There is no guarantee that you will run into correctness problems, but potentially you will run into correctness problems. And this is the mutual exclusion principle, basically. That's the invariant. And I will, again, posit that a multiprocessor should provide the correct execution of synchronization primitives to enable the programmer to protect shared data. So a programmer wants to do some synchronization in their parallel program, and they should be able to use a synchronization primitive, and they should be able to correctly protect their data. And that requires some hardware support, as we will see. Okay, so how do you support mutual exclusion? There's a programmer part of it. That's not what we're going to deal with. That's what you have dealt with in parallel programming, hopefully. You've hopefully seen many, many different synchronization mechanisms. Is that correct in parallel programming? Yes. Maybe you're bored of it. Maybe it's exciting, fine. But there are many of them, clearly. And we're going to assume that the programmer makes sure that mutual exclusion is correctly implemented in some way. And we will assume this. Threads are properly synchronized. But clearly, this is an important topic as well, right? As you have seen in parallel programming. Correct parallel programming is an important topic. And this is the seminal paper. Maybe you covered it in parallel programming. Did you guys cover this paper in parallel programming? Dijkstra's seminal paper, Cooperating Sequential Processes. It's a beautiful paper. You can find it online also in his old website. And he basically talks about Decker's algorithm for mutual exclusion as being correct, for example. He provides proofs of correctness, etc. We're going to use a similar algorithm in this next cooked up version of it. But basically, that's what we're going to assume. But we will also see that programmer relies on hardware primitives to support correct synchronization. If the hardware primitives are not correct or unpredictable, programmer's life is tough. And if hardware primitives are correct, but not easy to reason about, or not easy to program, then programmer's life is still tough. But maybe that's not a correctness problem. This is a correctness problem, and this is a usability problem. And they're both bad, let's say. One is worse than other, perhaps. And we're going to use this example. I'm going to assume that this program is correct. And you can make it correct, actually, by specifying the right things in this else portion. Okay, maybe that's not the best way of programming things, but this is an okay way of programming things. Okay, so what's happening here? We have a processor 1, processor 2, and they're both executing these two different threads. And only, there's a critical section, as you can see. Only processor 1 or processor 2 should be in the critical section at any time, not both. Okay, so what does processor 1 do? Initially, f1 is equal to 0. F1 basically says is the variable that indicates whether processor what is in the critical section. And you have a counter variable at processor 2 that indicates whether processor 2 is in the critical section. I mean, you can immediately say, okay, this is not how I program, maybe, fine. But if this is the way that the programmer programmed for whatever reason, and if they made it correct, and I think I would argue that you can make it correct easily, the hardware should still provide the guarantee that this should basically only P1 or P2 should be in the critical section. Let's see why. So processor 1, before entering the critical section, it sets F1 to 1. And then checks if the other processor is in the critical section. If not, then it enters the critical section. Before exiting, it sets F1 to 0. And if the other processor is in the critical section for some reason, it does the else, which basically does the management and retries, basically. So that's why the else portion is important for programming. And processor 2 does exactly the dual of this, basically. It sets F2 to 1 before entering the critical section and checks whether the other processor is in the critical section. If not, it enters. After it finishes the critical section, it sets F2 to 0, saying it's not in the critical section anymore, and then goes with its rest of the program. If the other processor was on the critical section, it does the else clause, which hopefully guarantees correctness, right? Okay. This sounds reasonable so far? Maybe this is not how you would program. This is probably not how I would program, but I would say that this is not a bad way of programming also. It's a version of Decker's algorithm in the end. So assume P1 is in the critical section. Intuitively, okay, if P1 is in the critical section, intuitively it must have executed A, right? Which means F1 must be 1, as A happens before B, right? Which means P2 should not enter the critical section. So this happens before logic. It's a very important logic. Again, Dijkstra introduced it in distributed systems. But basically, if this processor is in the critical section, A must have executed, and A happens before B, which means that P2 should not enter the critical section. Why? Because if A has executed, F1 is 1. Right? If this processor is in the critical section, if you find this processor also in the critical section, then you're violating the happens before logic from a global perspective. Does that make sense? Hopefully nothing is surprising here and you agree with this, right? Okay, so we'll see a violation of this. So basically, assuming some things you do in hardware, of course, right? Okay, so keep this in mind. I have another copy of it in case we need it, because we cannot really project multiple slides concurrently. We have a parallel processing problem. Yes?
At least in the way that it's currently written, isn't it possible to have a complete deadlock where if both P1 and P2 execute perfectly in sync and reach A and X at the same time, then neither will be able to pass B or Y? Because F1 will block Y and F2 will block B, and both will just infinitely be unable to access a critical section.
Yeah, potentially. You're relying on some timing basically over here. Yeah. So you're saying basically if both of them execute this synchronously, F1 and F2 are both 1. I see. Yeah. Yeah, potentially, yes. But you could solve that problem. I mean, you could break deadlocks, etc. Right? That's why I didn't want to go into all of those, because this program will be much more complicated otherwise. But that's a good point, basically. I mean, deadlock avoidance and detection is actually another interesting problem. Okay, but assume that the program works correctly. Okay, ignore that deadlock issue for now. Because even if that deadlock issue exists, there's another problem that I'm going to describe. And that deadlock issue you definitely need to solve. Okay, so the question is basically, can the two processors be in the critical section at the same time, given that they both obey the von Neumann model perfectly? And maybe it's good to think about memory in a different way. I mean, there are multiple reasons why the answer to this is yes, but I'm going to give you one potential reason. So for example, P1 and P2 may be connected to memory in some way, and there may be an interconnection network. And P1 and P2 may be connected to memory banks in this way. And P1 may be far away from some variable, as we will see over here. So P1 is here, F1 is here, P2 is here, F2 is here. And it takes some time to fetch the value of F1 for P1. It takes some time to fetch the value of F2 for processor 2. Okay, do I want to use the board, or do I want, maybe I'll go through this. So are you able to follow this? Okay, otherwise I'm going to spend some time over there and we may not be able to finish, but let's try to go through it. If you have any questions, let's start. So this is what we're going to assume. So this is the program, what it looks like, A and B. Processor 1 sets F1 to 1, and then F2, it checks if F2 is equal to 0 and enters the critical section. Processor 2 sets F2 to 1, checks F1 is equal to 0 and enters the critical section. And I'm going to give you one example of why they may both go into the critical section, and you can get an incorrect result. So let's take a look at this. Let's take a look at this timeline. So at time 0, what the processor 1 does is it sets F1 to 1, basically executes operation A. And processor 2 sets F2 to 1. Okay, let's finish processor 1 first. So at this point, F1 equals 1 is complete from the processor 1's view. Oh, low battery. I may need your thing right now. Otherwise, we're not gonna. Yeah, I think what I did wrong was I kept the right plug for you? Yeah, it's the right plug. Thanks. Assuming things over here work. So I think what happened was during the break, I didn't turn off my display this time, which was probably not the correct choice. And okay, now it's good. Thanks. Okay, so assume that processor 1, after doing this, it's F1 equals 1 is complete from processor 1's view. Processor 1 says, okay, I set F1 is equal to 1, and I send this F1 update to memory. But I can continue. I did the store. It's going to become visible to some other processor later on. But from my point of view, it's fine. I'm finishing this operation based on what the programmer said, von Neumann model, right? And it sends A to memory. Later, memory will complete A, as you will see. I guess that's the one advantage of having the full timeline over here. Memory will complete A much later. Okay, processor 2 does the dual of it, basically. It executes operation X, sets F2 to 1. At this point, F2 is equal to 1 from processor 2's point of view, and X is sent to memory. Remember, F2 and F1 are the variables that tell whether processor 1 and processor 2 are in the critical section. Right? Okay, and X is sent to memory. But that X is going to be updated much later in memory, before processor 1 and 2, before processor 1 loads it, or after processor 1 loads it. We will see that. Okay, at time 1, let's say in the next cycle, processor 1 now executes B. It tests whether F2 is equal to 0. And it doesn't have F2 because F2 is somewhere in memory, let's say. So it requests F2 from memory, and load from memory for F2 is started at this point. It'll take 49 cycles because F2 happens to be, I don't know, closer to processor 1, let's say, in terms of memory banks. Processor 2 does a dual. It basically is trying to test whether F1 is equal to 0. It sends requests for F1 to memory. And basically, from processor 2's perspective, load for F1 is started at this point. And it will complete 49 cycles later. So let's fast forward 49 cycles. Memory sends F2 which is equal to 0, because it didn't receive processor 2's update to F2 yet. Right? F2 is still equal to 0. Well, I should have said that earlier. But initially, F2 and F1 are equal to 0 in memory banks, as expected. So at cycle 50, memory sends F2's value to processor 1. And processor 1 finishes load of F2. Now processor 1 checks F2, the value is 0. So it can enter critical section. So it enters the critical section in the next cycle. Now it's executing the critical section. Now at cycle 50, processor 2 does the dual, which is, well, memory does the dual, let's say. Memory sends F1, whose value is 0 at memory still, to processor 2. And processor 2's load to F1 is complete, and the value is 0. And the next cycle, processor 2 says, oh, F1 is equal to 0. So I'm going to enter the critical section. And now both processors are in the critical section. Right? Why? Because there were dynamic latencies, and the updates for F1 and F2 did not arrive before the processors read F1 and F2. And that can certainly happen in a memory system. Yes.
Isn't this more of a problem for the memory controller, because if writes always happen before subsequent reads, then it's not a problem.
If writes, well, not necessarily. Recall the interconnection network. Memory controller may not see the operations in the order they were really intended. And then the question is, of course, what is the order that was really intended when you have multiple processors, right? So it's really about the delays, dynamic delays. So you cannot solve this in the memory controller.
I was thinking of the traditional model where we have a queue and then we queue up requests. So we have
that's assuming. So I think maybe we didn't really think about the interconnection network as much in that case, right? If everybody operates and everybody has access to that queue immediately, then yes, you can solve that problem. But if you want to build a scalable multiprocessor, that queue is going to be the bottleneck. So you actually want to really scale up to an interconnection network. So basically, there are delays in the interconnection network that lead to this problem in this case. But you can construct it actually without the delays also potentially. I'm going to let you think about that for now. Okay, so let's say at cycle 100, memory completes A. Remember, A was processor 1 setting F1 equal to 1. And F1 becomes 1 in memory, but it's too late now because processor 2 actually loaded F1 and assumed that F1 is equal to 0 and entered the critical section. Now, the dual of that happens in memory in cycle 100. Memory completes X, which is processor 2 setting F2 equals to 1 at cycle 100. Again, this is too late because processor 1 already loaded F2 much more quickly because it had faster access to that memory bank. That's the assumption. And as a result, it also went into critical section. So here's an example where processors individually do nothing wrong, right? Processors are actually doing exactly correctly. They're obeying the von Neumann model. If you look at the execution order, A is executed before B and completed. B is executed before the critical section and completed. This processor did nothing wrong. This processor, X is executed before Y and completed. Y is executed before the critical section and completed. This processor did nothing wrong. But the end result is you get something wrong. Well, why is it wrong, you would say? Because it violates what happened before, intuition and principle, basically. Well, if you look at P1's view of what happened, basically P1 and P2 saw an inconsistent order of operations in memory that violates what happened before intuition, right? What did P1 see? So this is exactly the same as what I drew over here. I'm waiting for this to go away, but maybe this is a better way. Okay, so what happened was processor 1's point of view, A happened before B, as it should, and B happened before X, right? Assume that this X did not become visible to processor 1, but fine, it happens over here. From processor 2's point of view, X happens before Y, and Y happens before A. And that's the order of operations from processor 1 and processor 2. And if you reduce it, processor 1's view is that A happens before X, processor 2's view is that X happens before A, and both cannot be correct, right? If you look at the global system, both cannot be correct from memory's perspective. Does that make sense? And this is why they happen before intuition is violated. And this is why you need to do something about it. Okay, I already said this, I think. Okay, basically the problem is that the processor did not see the same order of operations to memory, and the happened before relationship between multiple updates to memory was inconsistent between the two processors' point of view. As a result, each processor thought other was not in the critical section. Okay, hopefully you agree that this is a problem now. Was your question answered now?
Yeah, but now they access the same memory location, right?
Yes.
I thought the definition somehow contained that they access different locations.
Well, they're not completely different, right? If they're basically, if there's no synchronization, if communication, yes, I agree with you. But these are still different memory locations, right?
Sure.
Okay. So it's not about, okay, maybe I should clarify. It's not about a single memory location. It's about multiple memory locations in place. Does that make sense? Maybe that's more clear, yes. So cache coherence, as we will see, is about a single memory location. But here we have multiple memory locations in place, not necessarily completely independent memory locations. Okay, maybe I understand your concern right now, I think, better. Okay, so the question becomes, how can we solve the problem? And the idea that Lamport developed in 1979 paper is sequential consistency. And it's a very simple idea. All processors should see the same order of operations to memory. In other words, all memory operations happen in an order that's consistent across all processors. This order is called the global total order. It doesn't matter what the order looks like. As long as it's a consistent order that obeys the von Neumann model also of each processor, that's fine. That's the idea, basically. And the assumption is that within this global order, each processor's operations appear in sequential order with respect to its own operations. That's the von Neumann principle. And that's what the paper you're going to read. Well, you don't have to read it after I explain it, but I think it's good to read it still. Lamport basically has two properties. A multiprocessor system is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order. And the operations of each individual processor appear in the sequence in the order specified by its program. The first one is the more important part, clearly. Right? The second one is the von Neumann model. But the von Neumann model is necessary for sequential execution also, in this case, sequential consistency. If each processor doesn't obey the von Neumann model, then you run into other problems. So let's take a look at the first expression over here. The result of any execution is the same as if the operations of all the processors were executed in some sequential order. Okay, maybe I'll look at it in the next slide, because this means that there are multiple possible orderings that are all sequentially consistent, right? And again, this is a memory ordering model or a memory model. This has to be specified by someone. And instruction set architecture is probably the right place to specify it, or system architecture, however you would like to think about it. That manual, basically, that you get when you want to program a processor. That's the instruction set architecture or programmer's model. Okay, so basically, programmer's abstraction looks like this. Memory is a switch that services one load or store at a time from any processor. And all processors see the currently serviced load and or store at the same time. Right? This is a conceptual view. This is not how you would build hardware, perhaps, right? But this is a conceptual view. Each processor's operations are serviced in program order within this. So everybody sees what's going on in memory, and memory is servicing only one processor at a given time. And loads and stores are all exposed to everyone. So this means that there are many sequentially correct, consistent operation orders. So potentially correct global orders look like this in the previous examples that we saw. Remember A, B, X, Y? Okay, I don't know. If you don't remember, these were A, B, X, Y. So A is setting F1, B is checking F2, testing F2. X is setting F2, Y is testing F1, right? And as long as all processors see exactly the same order, these are all sequentially consistent. Right? In this case, there are 6 orders. And which order, or interleaving, this is also called an interleaving of memory operations. Unfortunately, interleaving is an overloaded term, but fine. This is observed, which order is observed depends on the implementation and the dynamic latencies, right? Okay, any questions? So let's take a look at what this implies, basically. Within the same execution, all processors see the same global order of operations to memory. So there's no correctness issue. We got rid of the correctness problem. And it satisfies it happened before intuition. But we didn't solve the debugging problem, meaning across different execution, different global orders can be observed. So all of these are possible, and all of these are sequentially consistent. And when you run the program once, you may see this order, meaning that one processor will get the lock before the other one. When you run the program again, you may see this order. Some other processor will get the lock first. And they may diverge from each other completely. So the execution over time may be completely different, so that what you did in the first run, or the bug that you got in the first run, may not appear in the second run. Right? So basically, debugging is still difficult. Each of these orderings are sequentially consistent, and they're perfectly valid, but order changes across runs. Yes?
Why is that last global order correct? It seems like that still allows both the threads to go into the critical section, because X executes X and Y, which will both report having unlocked critical sections.
No, that's not true. So, I mean, okay, let me go to X, Y, A, B. So you're talking about this X, Y, A, B, right? Yeah, let's go back to the program. Okay, I want to go through, okay. So X, Y, A, B means that, yeah, okay, you're fine now, right? Okay. If you violate the sequential ordering, then you will get the wrong thing, perhaps. But yeah, you don't violate that. Okay, so I don't need to cover it, right? Okay, good. Yeah, that's why you need multiple slides at the same time, I think. Or maybe better slides than what I have constructed. Okay. Okay, so hopefully this is clear so far. Now we have not discussed how to make this happen, right? Making this happen is clearly hardware cost now. You have a lot of parallelism inside memory, you have a scalable interconnect. Now you're reducing the operations to be observable by every processor in the same order. So this processor cannot have a shortcut to memory without anybody else seeing. That doesn't sound good, right? What if a processor does out-of-order execution internally? It loads some value much earlier. It tries to use that value. No. It cannot do that, because every operation should be visible at the same time to every processor. So how do you make that happen? How do you make out-of-order execution happen? How do you make prefetching happen? How do you make caching happen? How do you make a scalable interconnect happen? So this breaks down a lot of the things that you really want to do for high performance, basically. So usually the way sequential consistency is actually quite strong. That's why we're going to try to make it weaker. But one way of implementing sequential consistency is checking at the end, meaning somehow you need to check at the end whether to enforce the order. I'm not going to go into the details of it right now, but maybe when we talk about the weak ordering models, it'll become more clear. Okay, maybe I'm getting ahead of myself a little bit. So Lamport doesn't talk about, Lamport is not dealing with hardware basically. Lamport is dealing with semantics. Semantically, this is what should happen. He doesn't talk about, oh, this is bad for performance, etc. Let's make it correct first. And you can see that I would recommend reading it basically. I'm not going to read this because I already described it. Okay, but basically it's a nice abstraction for programming, but there are two issues. Basically, you have two conservative ordering requirements, and we will see why. Do you really want every single load and store to be visible to every processor? And we've already discussed this, right? What if the processors are not even communicating with each other? This sounds stupid then, right? If they're not even at some point synchronizing, it sounds stupid. So when do you really want this ordering? And people have asked this question, and when you really want this ordering is when you're synchronizing. So you don't want this ordering when you're not synchronizing, basically. So why not actually do this when you're actually synchronizing? And that's the idea. So we will see weak models, basically. So basically, it also limits the aggressiveness of performance enhancement techniques like we have discussed, right? If this is so strict, how do you make it work? And then that's the question, basically. Is the total global order requirement too strong? Do we need a global order across all operations and all processors? How about a global order only across stores? Well, this can be made to work. There's a total store order model. x86 actually does this. Well, I don't know if the recent versions of x86 does it, but x86 usually does total store ordering. It's also sometimes called the unique store order. I'm not going to go through all of the models over here. And in some cases, the literature is actually pretty bad here. If you try to read memory consistency papers, your head may explode because it's not really nicely and cleanly explained sometimes, I would say. Because they don't really tie. So Lamport paper is beautiful, right? It clearly ties the intuition. It says basically you violate the happen before relationship, right? And if you're a reasonable person, probably you should not violate the happen before relationship, right? Unless you can travel through time or something. But yeah, sometimes the literature is very hard to. But I'll give you, I think, some intuition as to how we can make this weaker. And this is the next one, basically. How about enforcing a global order only at the boundaries of synchronization? And this actually, I think, becomes much more interesting now. And these have led to relaxed memory models. A lot of the models are actually relaxed memory models in existing ISAs. I don't know if there are any big ISAs that enforce sequential consistency today. Are there? Maybe, you know, but I think you were going to ask a question. Yeah, go ahead, please.
Wouldn't it also be possible to like avoid these issues to do something on the memory controller side, such as it not servicing a request to something until, like, because the memory controller would know, for example, that processor B2 was doing a store for F2.
But how would the memory controller know if that message arrives much later to the memory controller? And this is similar to your colleague's question over here. Basically, if memory controller receives the messages as at the same time they're generated, yes, you can do something about it. But if the messages arrive at completely different times, then memory controller has no notion of what the ordering should be. Make sense? That was the case in the previous example, basically. Basically, the interconnect has different levels of delays over here. And there may be multiple memory controllers, certainly, right? Okay.
For that one, my thought was that it would get both write requests potentially at the same time, but it would be able to differentiate the request for F2 as coming 1 second or one time unit later than the write to F2, and therefore it would delay until the write was complete. But of course, that wouldn't work if it was requesting to read F2 at the same time as writing to F2 from the other side.
Yeah, exactly. Yeah. Yes, please.
Couldn't the memory controller just keep track of the operations it sends like 10 cycles beforehand and keep track of that? And if, for example, the next cycle in another processor, it's asking the same value, just hold it in, until the value from another processor comes back.
Now you're trying to solve the problem, I think. Yeah, I mean, you could try to do that. But for example, if you look over here, here memory sends F2 to processor 1, and memory receives F2 equals to 1 50 cycles later. Right? Oh, I see. Basically, there's a global timestamp. And yeah, okay, now you're getting to a solution, basically. I mean, in the end, this is a distributed system problem, basically. Certainly, yes, memory can do that. And basically, it can send a signal saying, oh, you did the wrong thing. I supplied the wrong value to you, right? Yes, but it may be too late. The processor may have retired a lot of instructions, right? So in a checkpoint recovery-based system, if the processor has checkpointed the state, yes, you could do that. Memory control says, oh, I sent the wrong thing to you. So wait. And in fact, that's a reasonable, potentially reasonable way of solving the problem, actually. And in general, when you want to support sequential consistency, you have to have some point of ordering of operations. And that point of ordering, unless that point of ordering says, okay, you can go ahead and finish the operation and retire it, you don't. That's one way of enforcing sequential consistency, actually, in hardware. So your solution is very similar to what may be done in real hardware. So you need buffering to be able to do that. Maybe not at the memory controller. Maybe you need to do it somewhere on chip, right? Send the messages to that while you're sending to the memory controller. That's what's done to get close to sequential consistency. But you can see that the buffering requirements could be very high, right? And the complexity can be very high. And also, you're delaying the processor now. The processor cannot retire the instruction until it's okayed by this unit that tries to resolve the order. Okay. Okay, very good. And there are a lot of other optimizations in literature that are kind of interesting to study. I'm going to give you one example paper that I will like soon. Okay. Okay, I think we've covered all of this. Okay, yeah, relaxed memory models and acquired release consistency model, which is an example of a relaxed memory model. So there's another issue with sequential consistency, which we discussed. Performance enhancement techniques could make an ST implementation difficult, or ST implementation may make these performance enhancement techniques not so performance enhancement anymore, let's say, because you need to wait to retire the operations. For example, out of order execution. Loads happen out of order with respect to each other and with respect to independent stores. This makes it difficult for all processors to see the same global order of all memory operations, right? Now, things are reordered, right? Caching and memory location is not present in multiple places. This prevents the effect of a store to be seen by other processors, right? So we will see tomorrow in cache coherence, there's an exclusive bit that you can have in your cache saying, I'm going to update this location and I'm not going to tell anyone about it in my cache. Now, this by definition violates sequential consistency, right? Because it prevents the effect of a store to be seen by other processors. As a result, it makes it difficult for the process to see the same global order. Now you can say, I'm not going to do that. Or you can say, I'm going to do that, but I'm also going to send a message to this unit. That's the ordering unit that basically is going to orchestrate what's going on if you want sequential consistency. Right? And that's perfectly valid. So you can actually make these mechanisms work by adding some complexity into the system, an ordering unit, for example. And that ordering unit can happen while caches are operating. And until the ordering unit says, okay, you're done with this operation, you're not done. You need buffering, basically, to get the benefits of these performance enhancement techniques. So let's talk about weaker memory consistency. This is based on the realizations that the ordering of operations is important when the order affects the operations on shared data. In other words, when processes need to synchronize to execute a program region. Okay, so this weak consistency, the idea is to have the programmer specify regions in which memory operations do not need to be ordered. Now you're putting some burden on the programmer, right? Programmer do this. But maybe again, if the programmer programs using disciplined synchronization mechanisms, compiler can do this task. So I think there is some ground over here. As long as the programmer, every single time they synchronize their program, they go through a library that's very well defined. The compiler can actually analyze everything, and compiler can communicate this to the hardware, as we will see. So memory fence instructions, for example. People actually use this in existing ISAs, right? These instructions delineate those regions. What do these instructions say? When you get to the fence, all memory operations before a fence must complete before the fence is executed. So it's basically enforces a precise point in terms of memory ordering. And you insert the fences at synchronization points. Basically, you get rid of the ordering sequential consistency requirements. Now fences need to be sequentially consistent, not all loads and stores. Okay, I said this already. All memory operations after the fence must wait for the fence to complete. But fences complete in program order, and all synchronization operations act like a fence. And what is missing over here is that fences need to be sequentially consistent. The ordering of fences need to be sequentially consistent. Otherwise, you run into the same problem that we ran into earlier. Makes sense, right? And this is the state of the art, let's say. This is what people, you have fence instructions in the ISAs today. And this is a seminal paper. I really like this paper. It talks about, well, there are multiple papers from the same group, actually. This is a group at Stanford. Kurosh-Garacholi's thesis was all about weak consistency models. This is one paper talking about 2 techniques to enhance the performance of memory consistency models. I'm going to give you the conclusion of the paper at the end. But basically, he covers, and with these nice explanations, sequential consistency is basically you have some ordering requirements, right? This arrow says V cannot perform until U is performed. And sequential consistency is everything, basically you have these ordering requirements being loads or stores, loads and loads, stores and loads, and stores and stores. There's a model that says store and load ordering can be relaxed. That's good, this processor consistency. Now let's take a look at this model. This actually becomes interesting, right? There's a model that's proposed by Dubois, weak consistency. You can see that there's an acquire, a lock, release a lock. There's an ordering between acquire and the critical section and release and critical section and acquire, but there's no ordering requirement within the critical section. Now there's no ordering over here, so that's great, right? So basically it guarantees a consistent view of memory only at synchronization points. And you can read this for yourself. Under SC, every access within the critical section is delayed until the previous access completes. Okay. Yeah, I mean, can you give me a couple of minutes, please?
Really stop
Yeah,
on time.
yeah.
Please.
Okay.
Please.
Okay. Well, it's
This one. You should
Yeah,
really
but-
stop on time. This is the rule at ETH.
but
Because
we're
I've also got to set up everything.
Yeah,
and
I
we are
know.
Also short of time.
I know, but we're almost about to finish here.
Yes, then this is the end of the lecture.
Okay.
Thank you for your
Okay. Well, you can see that there's a release consistency model, which basically makes sure that acquires and releases are ordered, but there's no ordering between critical sections and the releases over here. So I would ask you to take a look at these papers, and I think I've explained this over here, and we'll start tomorrow. Okay, so I think we will start tomorrow with the advantages and disadvantages of weaker consistency. And okay, maybe I'll cover the advantages also. So there's clearly no need to guarantee a very strict order of memory operations. This enables the hardware implementation of performance enhancement techniques to be simpler, and it can be higher performance than strict ordering. Disadvantage is that there's more burden on the programmer right now, as you can see, right? Or software. You need to get the fences or the labeling of these synchronization operations acquires and releases correct. Another example of the programmer microarchitect trade-off, right? Again, if you're programming using disciplined programming techniques, that's perfectly fine. The compiler can actually do this. Okay, I will let you read this, but you can see that 2 techniques that this paper talks about is prefetching and speculative execution. They basically say prefetching and speculative execution together can overcome the performance downsides of the consistency model. Basically, you can actually get, if you actually employ prefetching and speculative execution, when you combine them, these techniques alleviate the limitations employed by a consistency model on buffering and pipelining of memory accesses, thus significantly reducing the impact of memory consistency model on performance. This is amazing. This is a conclusion in 1991, about 20 years ago. Well, 30 years ago, sorry. There's been a lot of research that has been done on this topic, which has reached a similar conclusion, actually, over the course of 30 years. So I find this amazing, actually. So keep this in mind. This is a food for thought. It's always good to look at these old papers to really understand Like, what is the fundamental result over here? Okay. So these are some example questions that you can find on the exam. In fact, they're in your homework. But so we're at the end of memory ordering right now. Any questions? Any burning questions, I should say? You have a burning question?
No. So.
Okay, going once, twice. Okay, you have a burning question. Well, up to you. Go ahead.
Quick one. Just without the retouching and speculation,
Uh-huh.
how fast is how much? I guess like what is the delta you? Yeah, without retouching.
Uh-huh. Yeah. Yeah, so that's a great question, basically. Without employing all of these techniques, what kind of difference that you get? And you have to read the papers, basically, for that. There is actually a significant difference. But if you do prefetching out-of-order execution, then you actually close the gap, and the models are becoming very close to each other, basically. Okay, I'll see you tomorrow when we talk about cache coherence. Take care.